Welcome to What is Big Data? After watching this video, you'll be able to explain big data, identify the characteristics of big data, and explain the 5 V's of big data. Bernard Marr, the analytics, KPI, AI, and big data guru, defines big data as the digital trace, or data, that we are generating in this digital era. To understand big data, we need to compare it with small data. Small data is available in limited quantities that can easily be interpreted by humans with little or no digital processing. Sports scores and employee shift schedules are some examples of small data. It is accumulated slowly and may or may not get updated continuously. Storing small data is relatively easy, as it is mostly available in a structured format such as first and last name, address, gender, and so on. And it can be maintained within an enterprise's own infrastructure or in a data center. Big data, on the other hand, is generated in massive volumes and has little or no structure in which it is received. Examples of semi-structured data include social media posts that could be images accompanied by hashtags, while unstructured data could include medical records from millions of patients. It's complex and requires specialized programs to interpret and make it available for human consumption. Not only is big data massive in size, it is collected continuously and grows exponentially in a short amount of time. Big data could be in any form, including but not limited to text, images, audio, and videos. Finally, big data is so voluminous that it is stored in the cloud or on server farms set up specifically for this purpose. It's a common misconception that big data refers to just large volumes of data. In reality, big data is the entire life cycle of working with large volumes of data. Let's take a look at each phase in the big data life cycle. Big data collection is initiated as a result of a business problem or requirement. As data is collected, it gets stored using a framework for distributed storage, such as Hadoop HDFS. To make sense of all the data collected, map and reduce tasks and scripts create a data model to store it in a database. This data model includes the various data entities, or objects, and the relationship and rules between these entities. After modeling, data is ready to be processed. Tools such as Apache Spark are used to produce meaningful information from the modeled data. Finally, the processed data is visualized and presented in a graphical format such as charts and graphs. This visualized data is then used for making meaningful business decisions and lead to new business cases, thereby creating a continuous life cycle. The research firm Gartner defines big data as a high-volume, high-velocity, and high-variety information asset that demands cost-effective and innovative tools for processing. Let's take a moment to appreciate just how huge big data volumes really are. You have probably heard of megabytes, gigabytes, terabytes, and possibly even petabytes, but big data can be even bigger. Do you know you can store over 11 million movies in 4K resolution in just 1 exabyte of space? Now visualize this. Modern computers generally ship with 1 to 5 terabyte hard drives. 1 zettabyte contains 1 billion terabytes, while a yottabyte fits in 1 trillion terabytes. Doesn't that boggle the mind? When we talk about big data, we traditionally talk about the 4 V's of big data. These are velocity, volume, variety, and veracity. Velocity is the speed at which data arrives. Volume is the increase in the amount of data stored over time. Variety is the diversity of data. Many forms of data exist and need to be stored. Veracity is the certainty of data. With a large amount of data available, how will we know if the data collected is accurate or inaccurate? These 4 main components are used to describe the dimensions of big data. Velocity signifies that data is being generated extremely fast, and the process never stops. Data must be processed quickly so that decisions can be made at the speed with which the data arrives. Velocity's main attributes are batch, close to real time, and streaming. What are the drivers? Definitely improving connectivity and hardware. Just think about all the devices that are connected through the internet today and all of the super fast response times. Big data also supports upscaling of pre-calculated analysis. Volume is the increase in the amount of data stored. The amount of big data generated is vast compared to traditional data sources. Volume attributes of big data are petabytes, exa, and zeta, to name just a few. Typical drivers of volume in big data are the increase in data sources, higher resolution sensors, and scalable hardware infrastructure. Variety is the diversity of the data. Data is generated by people and processes through the use of machines from both inside and outside an organization. Some of the data is structured and semi-structured, but most is unstructured. The main attributes are structure, complexity, and origin. Drivers of variety in big data can be mobile technologies, scalable hardware infrastructure, resilience, fault recovery, efficient storage, and retrieval. Veracity is the quality, origin, and conformity to facts and accuracy of the data. This is because data comes from both within and outside an organization. Attributes include consistency and completeness, integrity, and ambiguity. Drivers of veracity in big data are cost and the need for traceability, robust ingestion, and extract, transform, load ETL mechanisms. Big data has another V that must be considered. The fifth V of big data is value. It is the outcome of making intelligent business decisions from leveraging the previous four Vs. The ultimate goal of an organization is to produce value in the form of faster and smarter business decisions, increase efficient use of resources, and discover new market opportunities. Big data supports innovation and thus creates value. In this video, you learned that big data is the digital trace that gets generated in this digital era. Big data is a high-volume, high-velocity, and/or high-variety information asset that demands cost-effective and innovative tools for processing. The core features of big data are the four Vs: velocity, volume, variety, and veracity. Big data creates a fifth V, value, when collected, stored, and processed correctly. Welcome to Impact of Big Data. After watching this video, you'll be able to list examples of big data-related technologies, explain the impact of big data on businesses and people, describe the Internet of Things, IoT, and its impact on big data. Big data is one of the most important subjects of this century. Yet globally, millions of people are generating and using big data without necessarily being aware of it. This personal data, in the form of photos, videos, and text that people send to each other, forms the bulk of data collected by consumer goods companies. So, it is interesting to consider how big data is impacting businesses and people. Have you ever searched for or bought a product on Amazon? Did you notice that Amazon's recommendations are based on what the users have searched for, have bought in the past? The items they have in the virtual shopping cart, items they have rated and liked, and what other customers have viewed and purchased. Companies like Amazon, Netflix, and Spotify use algorithms based on big data to make specific recommendations based on customer preferences and historical behavior. Recommendation engines are a common application of big data. Personal assistants like Siri on Apple devices or Alexa on Amazon devices use big data to devise answers to the infinite number of questions end users may ask. These assistants use some of the most advanced neural networks ever made. This allows them to process speech into text and translate text into complex tasks that can be carried out across multiple applications within that device. Sources of big data collected for these actions include not only personal data and preferences on device and in the cloud, but also external factors. Google Now, for example, makes recommendations before users ask for them, especially when it is linked to the user's calendars and location, and sensing is enabled on the user's phone. Google now knows where the user is and where they need to be. It can tell users about things like traffic or the weather before they even ask for it. In this instance, the collection of big data is used to forecast future needs and behavior. Now that we have an idea of how consumers are using big data, let's take a look at how big data is impacting businesses. Clive Humby went as far as to call data the new oil, and Jeffrey Moore compared the value of data to our senses of sight and hearing. Big data is fundamentally changing the way businesses compete and operate. Complex and powerful machine learning algorithms drive business decisions that ultimately increase effectiveness. In recent years, the annual demand for data scientists and big data engineers is increasing significantly, and the big data skill set remains highly valuable to businesses. The Internet of Things, IoT, refers to a system of physical objects that are connected through the Internet. A thing or device can include a smart device in our homes or a personal communication device such as a smartphone or computer. These collect and transfer massive amounts of data over the Internet without any manual intervention by using embedded technologies. All of these devices gather, analyze, share, and transmit data in real time. Without big data, IoT devices would not hold the functionalities and capabilities which have gained them so much attention globally. Following Statista's forecast, we will see 4 times more IoT devices than the total number of the entire world population by 2030. Let's look at major components of the IoT ecosystem. An Internet-enabled connected network of systems that comprise smart devices and sensors constantly produce and transmit a variety of data. This big data is passed through a gateway that routes it to its destined storage in the cloud. Data engineers use sophisticated algorithms to make sense of this collected big data and compile it into an analytical form that can be interpreted by humans. The analyzed data is then used to make business and consumer decisions to enhance the customer experience and to enhance productivity. For example, a security camera could continually upload footage, and a cloud-based big data algorithm may alert the user if any activity is detected. In this video, you learned that big data is everywhere and is being collected and used to drive business decisions and influence people's lives. Virtual personal assistants like Siri on Apple devices or Alexa on Amazon devices use big data to devise answers to the infinite number of questions end users may ask. Google now impacts people through using big data to forecast future needs and behavior. Internet of Things, IoT devices continually generate massive volumes of data, and big data analytics helps companies gain insights from the data collected by IoT devices. Welcome to Parallel Processing and Scalability for Big Data. After watching this video, you'll be able to explain why big data requires parallel processing, identify the differences between linear and parallel processing, identify why parallel processing is apt for big data, explain parallel processing and scalability, describe the motivation for horizontal scaling, demonstrate embarrassingly parallel, explain fault tolerance in parallel computing. You can do lots of things with data at various sizes, right? In any normal analytics cycle, the functionality of the computer is to store data and move that data from its storage capacity into a compute capacity, which includes memory, and back to storage once important results are computed. With big data, you have more data than will fit on a single computer. Parallelism, or parallel processing, can best be understood by comparing it to linear processing. Linear processing. Linear processing is the traditional method of computing a problem where the problem statement is broken into a set of instructions that are executed sequentially till all instructions are completed successfully. If an error occurs in any one of the instructions, the entire sequence of instructions is executed from the beginning after the error has been resolved. It's evident from the processing method that linear processing is best suited for minor computing tasks and is inefficient and time-consuming when it comes to processing complex problems such as big data. Parallel processing. The alternative to linear processing is parallel processing. Here, too, the problem statement is broken down into a set of executable instructions. The instructions are then distributed to multiple execution nodes of equal processing power and are executed in parallel. Since the instructions are run on separate execution nodes, errors can be fixed and executed locally, independent of other instructions. As noted on the previous slide, parallel processing offers significant advantages when dealing with complex problems such as big data. Some of the other benefits of using parallel processing are reduced processing times. Parallel processing can process big data at a fraction of the time compared to linear processing. Less memory and processing requirements. Since the problem instructions are executed on separate execution nodes, memory and processing requirements are low even while processing large volumes of data. Flexibility. The biggest advantage of parallel processing is that execution nodes can be added and removed as and when required. This significantly reduces infrastructure cost. Data scaling is a technique to manage, store, and process the overflow of data. You can get a larger single-node computer, but when your data is growing exponentially, eventually it will outgrow the capacity that is available. Increasing the capacity of a single node as a means of increasing capacity is called scaling up. A better strategy, or at least the one most people ultimately choose, is to scale out or to scale horizontally. This simply means adding additional nodes with the same capacity until the problem is tractable. The individual nodes arranged in this way are called a computing cluster. Compute clusters can solve problems that are known as embarrassingly parallel calculations. These are the kind of workloads that can easily be divided and run independent of one another. If any one process fails, it has no impact on the others and can easily be rerun. An example would be to, say, change the date format in a single column of a large data set that has been split into multiple smaller chunks that are stored in different nodes of the cluster. Sometimes, sorting a large data set adds significant complexity to the process. Now, the multiple computations must coordinate with one another because each process needs to be aware of the state of its peer processes in order to complete the calculation. This requires sending messages across a network to each other or writing them to a file system that is accessible to all processes on the cluster. The level of complexity increases significantly because you are basically asking a cluster of computers to behave as a single computer. Most calculations in enterprise environments are considered embarrassingly parallel, with some not-so-easy calculations. While this statement is true to varying degrees, it has guided the design of underlying frameworks. In the Hadoop ecosystem, the concept of bringing compute to the data is a central idea in the design of the cluster. The cluster is designed in a way that computations on certain pieces or partitions of the data will take place right at the location of the data when possible. The resulting output will also be written to the same node. Computers break, outages happen, and you need to be prepared. In such cases, fault tolerance comes into play. Fault tolerance refers to the ability of a system to continue operating without interruption when one or more of its components fail. This works for Hadoop Primary Data Storage System, HDFS, and other similar storage systems, like S3 and object storage, a system like the one we showcase here. Consider the first three partitions of a data set labeled P1, P2, and P3, which reside on the first node. In this system, copies of each of these data partitions are also stored on other locations or nodes within the cluster. If the first node ever goes down, you can add a new node to the cluster and recover the lost partitions by copying data from one of the other nodes, where copies of P1, P2, and P3 partitions are stored. Clearly, this is an extraordinary complex maintenance process, but the Hadoop file system is a robust and time-tested framework. It can be reliable to 5 nines, 99.999%. In this video, you learned that big data requires parallel processing on account of massive volumes of data that are too large to fit on any one computer. Linear processing is sequential, while parallel processing works on multiple instructions at the same time. Parallel processing has significant advantages over linear processing, and it is best suited for processing big data. Parallelism in big data is parallelization across multiple processors in parallel computing environments. It focuses on distributing the data across different nodes operating on the data in parallel. Horizontal scaling, or scaling out, is a strategy to increase the capacity of a single node as a means of increasing capacity. Embarrassingly parallel calculations are the kinds of workloads that can easily be divided and run independently of one another. If any one process fails, it has no impact on the others and can simply be rerun. Fault tolerance is the property that enables a system to continue operating properly in the event of the failure of some of its components. Welcome to Big Data Tools and Ecosystem. After watching this video, you'll be able to identify the key tooling categories within the big data ecosystem, describe the role of each tooling category in the big data lifecycle, list major tools and vendors within each big data tooling category. Big data tools have 6 different categories: data technologies, analytics and visualization, business intelligence, cloud service providers, NoSQL databases, and programming tools. Let's take a look at each of these components in detail. Data technologies are specially designed to analyze, process, and extract meaningful information from big data. These functions are beyond the capabilities of traditional data processing tools. These technologies capture, process, and share big data work with structured and unstructured data and offer high-performance parallel processing of big data. Data technologies for big data are dominated by open-source projects, including Apache Hadoop, Apache HDFS, and Apache Spark. Major commercial vendors such as Cloudera and Databricks contribute to and support these projects. Data analytical tools examine large amounts of data to uncover hidden patterns, correlations, and trends. Data visualization, on the other hand, provides a visual representation of these trends in the form of graphs, charts, and maps. These tools provide an accessible way to view and understand trends, outliers, and patterns in data. Tableau, Palantir, SAS, Pentaho, and Teradata are leading examples of analytics and visualization tools. It's not enough to only analyze the visualized data. Business intelligence tools transform raw data into meaningful, actionable information that is suitable for business analysis. Business intelligence techniques also involve basic mathematical concepts such as probability, statistics, and flowcharts. The insights gained from business intelligence help drive business decisions. Some examples of BI tools are Cognos, Oracle, Power BI, Business Objects, and Hyperion. Big data presents challenges to storing, transporting, processing, mining, and serving enormous amounts of data. Cloud providers offer fundamental infrastructure and support with shared computing resources, including computing, storage, networking, and analytical software. Cloud providers also provide software-as-a-service models with point solutions to allow enterprises to easily aggregate, process, and visualize data. Examples of cloud service providers include AWS, IBM, GCP, and Oracle. Another key component of big data commercial tools are NoSQL databases that are tailor-made for big data processing. NoSQL databases are built from the ground up to store and process vast amounts of data at scale and support a growing number of modern businesses. NoSQL databases store data in documents rather than relational tables. Types of NoSQL databases include pure document databases, key-value stores, wide column databases, and graph databases such as MongoDB, CouchDB, Cassandra, and Redis. Programming tools are the final component of big data commercial tools. These programming tools perform large-scale analytical tasks and operationalize big data. They also provide all necessary functions for data collection, cleaning, exploration, modeling, and visualization. Some popular tools you can use for programming include R, Python, SQL, Scala, and Julia. In this video, you learned that there are 6 main components of big data tools, namely data technologies, analytics and visualization, business intelligence, cloud providers, NoSQL databases, and programming tools. Each tooling category plays a very specific and critical role in the big data lifecycle. Several major commercial and open source vendors provide tools and support for big data processing. Welcome to Open Source and Big Data. After watching this video, you'll be able to explain the role of open source in big data, describe platforms for coordinating open source, describe the most popular open source frameworks. What is an open source software? A simple definition of an open source software is that it is free. Not only is the runnable version of the code free, but the source code is also completely open, meaning that every line of code is available for people to view, use, and reuse as needed. However, a project becomes truly open source once it embraces the open governance model. This action ensures that any contributor from any organization can propose changes to the code, and the overall project can be steered to serve the community's needs. It's important to note that not all open source software is the same. The type of license associated with the software prescribes how you can use it. Before using any open source software, it is important to check for the type of license it's available under and to understand the permissions available under the specific license type. Accordingly, we need to ask, why is the open source model used for big data? Open source projects are massive efforts. While many projects are started within one organization, the truly open source projects persist beyond the efforts of any single organization. These projects form the foundation of all the modern big data infrastructure. Consider the Linux kernel. When Linus Torvalds first began developing this kernel as an open source, there were many players in the operating system space, and many were offering only proprietary versions of their code. It was not clear at the time who would ultimately emerge as the OS standard. Nearly 30 years later, Linux is the standard for all servers. This is true for almost every data server in every part of the world, regardless of hardware, software, or service provider. This happened because the project took on a life of its own beyond any single company's interest and persists beyond any one organization's cycles of interest. The open source development model is to software development what democracy is to the government. It is the most transparent way to conduct a project and ultimately serves the will of the people participating in it. In some senses, it is a surprising result that a completely open model will ultimately be a more profitable solution. But this has proven to be the case time and time again, and we now embrace the model without controversy. Most open source projects have formal processes for contributing to code and also include various levels of influence and obligation to the project. Committer, contributor, user, user group. Typically, committers have the ability to modify the code directly, while contributors submit their code for review by a committer before the code is modified. Many more people are simply users of the code. Most, but not all, major open source projects belong to one of the major open source foundations and follow a similar governance procedure. Open source means that the code is freely visible, which is an important distinction from proprietary software. Open governance, however, is what makes the project truly open and democratic. Open source foundations prescribe best practices for open source development as well as open governance. The biggest component of big data is, by far, the Hadoop project and its 3 main components: MapReduce, the Hadoop file system, HDFS, and the resource manager, Yarn. MapReduce is a framework that allows code to be written to run at scale on a Hadoop cluster. It is still used, but not as much as more modern big data computation frameworks like Apache Spark. HDFS is the file system that stores and manages big data files. It manages all of the issues around large and distributed data sets, including resilience and partitioning. It is still a mainstay of the industry. 70% of the world's big data resides on HDFS. More modern approaches to distributed storage, such as S3 and object storage, are coming into use, but they are based on the design principles of HDFS. Yarn is the resource manager that comes with Hadoop, and it is the default resource manager for many big data applications, including Hive and Spark. It is one of the most robust resource managers in use today, but more modern container-based resource managers, like Kubernetes, are slowly becoming the new de facto standards. Concluding, these are the main components of the Hadoop ecosystem, and most big data applications are built on top of them. The array of big data applications available to the user is dizzying. They all build upon the basic Hadoop framework or interact with it in some way, however. Frameworks like Hive and Spark support lots of ETL, extract, transform, load, and computation tasks on Hadoop systems. Some systems that integrate tightly with the Hadoop ecosystem are Apache HBase, which is a large NoSQL data store. It manages storage and computation resources outside of the Hadoop ecosystem, but often reside on the same cluster. Open source packages like the Hortonworks Data Platform, HDP, provide a set of big data tools that are already configured to work together and include most of the important open source packages, Hadoop, Spark, Hive, HBase, and others. In this video, you learned that open source runs the world of big data. Open source projects are free and completely transparent. The biggest component of big data is, by far, the Hadoop project, including MapReduce, HDFS, and Yarn. Open source has big data tools like Apache Hive and Apache Spark. Welcome to Beyond the Hype. After watching this video, you'll be able to describe facts about big data, describe the key sources of big data, explain different types of big data, describe the contribution of cloud computing in big data. So, why is everyone talking about big data? More data has been created in the past 2 years than in the entire previous history of humankind. There is a 40% projected growth in global data generated per year. By 2026, the amount of digital data created will exceed twice the amount of data created since the advent of digital storage. The chart on the right shows the growth in global data in zettabytes. There are 3 major sources of big data. Social data comes from the likes, tweets and retweets, comments, video uploads, and general media that are uploaded and shared via the world's favorite social media platforms. Machine-generated data and business-generated data are data that organizations generate within their own operations. Machine data is defined as information which is generated by Internet of Things, IoT, sensors-equipped industrial equipment that are installed in machinery, and even weblogs that track user behavior. Transactional data is generated from all the daily transactions that take place both online and offline, such as invoices, payment orders, storage records, delivery receipts. Big data comes in 3 types: structured, semi-structured, and unstructured data. Structured data is data that is organized, labeled, and has a predefined data model that conforms to a tabular format. Common examples of structured data includes names, dates, addresses, and credit card numbers. Unstructured data is said to make up about 80% of data in the world and does not conform to any predetermined format. It includes images, audio or video files, sensor data from IoT devices, text messages, and social media posts. Semi-structured data includes components of both structured and unstructured data in that it is mostly unstructured, but includes some metadata that identifies certain characteristics. Emails fall into the category of semi-structured data because while the content in an email is usually unstructured, there are several characteristics such as the email addresses, subject line, logo images, and URLs that can be pulled into structured tables. Some sources of structured big data are relational databases and spreadsheets. With this type of structure, we know how data is related to other data, what the data means, and the data is easy to query using a programming language like SQL. Some sources of semi-structured big data are XML and JSON files. These sources use tags or other markers to enforce hierarchies of records and fields within data. Currently, there is an explosion of data coming from Internet activity, and in particular, video production and consumption, as well as social media activities. These numbers will just keep growing as Internet speeds increase and as more and more people all over the world have access to the Internet. The emergence of cloud computing has contributed significantly to the launch of the big data era. Cloud computing allows users to access highly scalable computing and storage resources through the Internet. By using cloud computing, companies can use server capacity as needed and expand it rapidly to the large scale required to process big data sets and run complicated mathematical models. Cloud computing lowers the price to analyze big data as the resources are shared across many users who pay only for the capacity they actually use. In this video, you learned that big data creation is growing at an exponential rate. Data types include social, machine, and transactional generated data. Big data is collected in structured, unstructured, and semi-structured forms. Advances in cloud computing have contributed to the increasing potential of big data. Welcome to Big Data Use Cases. After watching this video, you'll be able to identify industries where big data is leveraged, discuss and outline the usage of big data in key industries. Data is getting generated at unprecedented volumes, and data-driven companies can develop a competitive edge over their peers if the data can be aggregated and analyzed effectively to generate breakthrough insights. Every major industry is taking advantage of data insights to improve decision-making, enter new markets, and deliver better customer experiences. Looking at industry trends, it is no surprise that financial services, technology, and telecommunications companies are the leading users of big data. This is where most of the innovation is currently taking place. These industries are closely followed by retail, government, healthcare, advertising and entertainment, and the gaming industry. Finally, data services, energy and utilities, system integrator consulting, shipping, and transportation round out the top industries that leverage big data. Let's now take a look at how some industries are leveraging the insights gained from big data analytics. In the retail industry, key uses of big data include price analytics and sentiment analysis. Price analytics helps understand market segmentation, identify the best price points for a product line, and perform margin analysis for maximum profitability. On the other hand, sentiment analysis leverages social media conversations to understand what consumers think of a product and subsequently to devise an effective marketing strategy to connect with the customers. Insurance companies use big data for fraud analytics. Big data helps them spot fraudulent claims and detect any anomalies in trends and prevent suspicious activities. Insurers also perform risk assessments using big data. For example, they may use predictive modeling based on user history and behavioral analytics to identify customers at higher risk of getting into accidents or having their vehicle stolen. Telecom companies are some of the top users of big data analytics. They use big data for improved network security. Machine learning-based pattern analysis identifies any threats to the network, and predictive maintenance resolves these threats before any serious damage to the network. Contextualized promotions based on user locations are another way telecoms leverage big data. For example, if a user is near a specific restaurant around lunchtime, they may receive a discount coupon for that restaurant, thereby increasing conversion rates. Telecoms continuously monitor their network for traffic patterns that would soon impact customer experience. Analytics alerts them on when is the right time to upgrade the network, thereby helping them focus investment for maximum returns. Telecoms also run pricing promotions based on real-time factors. These promotions are tested with targeted customer groups to produce optimized pricing packages. In manufacturing, big data helps with predictive maintenance of machines. The data from sensors are used to analyze equipment usage patterns to predict equipment failure, maintenance requirements, and parts replacement. Big data is also used to optimize production by using AI algorithms to understand production lines and recommend optimizations where production time is higher than necessary. From supply chain analytics to targeted marketing, traffic management, and insurance premiums, the automotive industry relies heavily on big data. Automobile service is a high-revenue area for manufacturers. Companies are predicting breakdowns and bringing in customers for repairs based on sensor data. Preemptive parts ordering reduces customer wait times and increases customer satisfaction. Real-time data harnessed from connected cars is driving the self-driving car and truck industry. The vehicle can make real-time adjustments to speed and direction based on the data it constantly gathers from its surroundings. Like the insurance companies, financial companies use big data for fraud detection and risk assessment. Other use cases for big data in finance include customer segmentation. By grouping customers into distinct segments, such as demographics, periodicity of transactions, social media, and customer service interactions, companies offer deeply personalized and targeted solutions to their customers. Algorithmic trading is another major area where big data is used extensively. Often, financial transactions are time-sensitive and use mathematical predictive models. Therefore, these are the perfect candidates to apply machine learning to make quicker and constantly improving decisions. In this video, you learned that companies are relying heavily on big data to differentiate themselves from the competition, and there are several ways in which the retail, insurance, telecom, manufacturing, automotive, and finance industries are leveraging big data to reduce cost, increase customer satisfaction, and make competitive business decisions. Welcome to Introduction to Hadoop. After watching this video, you'll be able to define Hadoop, explain the history of Hadoop, list reasons why Hadoop was the answer to big data processing, outline some of the challenges of Hadoop. Hadoop is an open-source framework used to process enormous data sets. Imagine this scenario. You have 1 gigabyte of data that you need to process, perhaps customer sales records or survey responses. The data is stored in a relational database on your desktop computer or laptop. Neither device has a problem handling this data set, and you can query the data with ease. You have a great year, and you pick up a few more clients. Your company starts growing very quickly, and that data grows to 10 gigabytes. Then 100 gigabytes. You pick up a big client, a retailer perhaps, with multiple databases. Maybe you're a mine manager, and a new executive decision means that you must now start processing data from equipment, front-end loaders, excavators, and haul trucks. You also have data about the environment, data about soil and weather, and data about safety and rock samples. Or perhaps your company is a delivery service, and you attach sensors to your entire fleet. Overnight, your clients, drivers, and their vehicles all start gathering data that you need to process. When your data grows from 1 terabyte to 10 terabytes and then 100 terabytes, you are again quickly approaching the limits of your local computers. And maybe you need to process unstructured data coming from sources like Facebook, Twitter, sensors, and so on. The senior leadership team at your company wants to derive insights from both the relational data and the unstructured data in order to make informed decisions. And they want this information as soon as possible. How can you accomplish this task? Hadoop might be the answer. Now, let's rewind. Before we use Hadoop to solve the problems, let's understand what Hadoop is. Hadoop is a set of open-source programs and procedures which can be used as the framework for big data operations. It's used for processing massive data in distributed file systems that are linked together. It allows for running applications on clusters. A cluster is a collection of computers working together at the same time to perform tasks. It should be noted that Hadoop is not a database, but an ecosystem that can handle processes and jobs in parallel or concurrently. Hadoop is optimized to handle massive quantities of data, which could be structured, tabular data, unstructured data, such as images and videos, or semi-structured data, using relatively inexpensive computers. In the 1990s, coming into the new millennium, the web grew significantly to millions of pages and different structures of data. Automation was needed to help handle simultaneously the differences in data structure and the web searches. In 1999, the Apache Software Foundation was established as a nonprofit. In 2002, the Nutch web search engine was created by Doug Cutting and Mike Carafella. Nutch was created on the basis that it could handle multiple tasks across different computers at the same time, while storing and processing the data in a distributed way so that the most relevant search would be returned faster. In 2006, Cutting joined Yahoo with the Nutch project, and the project was divided into the web crawler and distributed processing. The distributed processing segment was called Hadoop, and in 2008, Yahoo released Hadoop to the Apache Software Foundation. Data is now in petabytes and exabytes, and big data is the term used to explain the complexity of the data. Hadoop has individual components for storing and processing data. The term Hadoop is often used to refer to both the core components of Hadoop as well as the ecosystem of related projects. The core components of Hadoop include Hadoop Common, which is an essential part of the Apache Hadoop framework that refers to the collection of common utilities and libraries that support other Hadoop modules. There's a storage component called Hadoop Distributed File System, or HDFS. It handles large data sets running on commodity hardware. A commodity hardware is low specifications industry-grade hardware and scales a single Hadoop cluster to hundreds or even thousands. The next component is MapReduce, which is a processing unit of Hadoop and an important core component to the Hadoop framework. MapReduce processes data by splitting large amounts of data into smaller units and processes them simultaneously. For a while, MapReduce was the only way to access the data stored in the HDFS. There are now other systems like Hive and Pig. And the last component is Yarn, which is short for Yet Another Resource Negotiator. Yarn is a very important component because it prepares the RAM and CPU for Hadoop to run data in batch processing, stream processing, interactive processing, and graph processing, which are stored in HDFS. The drawbacks of Hadoop could not be left unnoticed by developers. Hadoop contained many smaller components. Although efficient at first glance, Hadoop failed at simple tasks. Hadoop is not good for processing transactions due to its lack of random access. Hadoop is not good when the work cannot be done in parallel or when there are dependencies within the data. Dependencies arise when record 1 must be processed before record 2. Hadoop is also not good for low latency data access. Low latency allows small delays, unnoticeable to humans, between an input being processed and the corresponding output providing real-time characteristics. This can be especially important for internet connections utilizing services such as trading, online gaming, and voice over IP. Hadoop is also not good for processing lots of small files, although there is work being done in this area, such as IBM's Adaptive MapReduce. Lastly, Hadoop is not good for intensive calculations with little data. To deal with the shortcomings of Hadoop, new tools like Hive were built on top of Hadoop. Hive provided SQL-like query and provided users with strong statistical functions. Pig was popular for its multi-query approach to cut down the number of times that the data is scanned. In this video, you learned that Hadoop is an open-source framework for big data. The core components of Hadoop are HDFS, MapReduce, Yarn, and Hadoop Common. The drawbacks of Hadoop outweighed the benefits. Welcome to Introduction to MapReduce. After watching this video, you'll be able to explain the terms map and reduce in MapReduce, describe why we use MapReduce, list the components of MapReduce, outline examples of common use cases of MapReduce. What is MapReduce? MapReduce is a programming model that enables massive scalability across hundreds or thousands of servers in a Hadoop cluster. As the processing component, MapReduce is the heart of Apache Hadoop. MapReduce is a processing technique and a program model for distributed computing. It is based on Java. Distributed computing is a system or machine with multiple components located on different machines. Each component has its own job, but the components communicate with each other to run on one system to the end user. The MapReduce algorithm consists of two important tasks, map and reduce. Many MapReduce programs are written in Java. MapReduce can also be coded in C++, Python, Ruby, R, and so on. As the name suggests, the MapReduce framework contains two tasks, map and reduce. Map takes in an input file and performs some mapping tasks by processing and extracting important data information into key value pairs, and these are the preliminary output list. Some more reorganization goes on before the preliminary output is sent to the reducer. The reducer works with multiple map functions and aggregates the pairs using their keys to produce a final output. MapReduce keeps track of its tasks by creating unique keys to ensure that all the processes are solving the same problem. Let's look at the framework visually. First, we have the map step, which takes a set of data and converts it into another set of data, where individual elements are broken down into key value pairs. The key is the name, and the value is the content. The input data is a file that is saved in the Hadoop file system called HDFS. Now let's assume we have an input file that contains names of people, and we would like to do a word count on the unique name occurrences. First, the data is split into the following 4 files, each of them in key value pairs and are worked on separately. For example, for the first split line for Teju and Brianna, we have 2 key value pairs with 1 occurrence in each file, and it will do the same for all key value pairs. We then have the reducer. The reducer processes the data that comes from the map. After processing, it produces a new set of outputs, which will be stored in the HDFS. The reducer starts with shuffling. Shuffling sorts the key and a list of values in a list. For example, you will see the key Teju and a corresponding list of values from the previous step. We will have Teju 111. This is because the name Teju occurred 3 times in the map step. It does the same for the rest of the names, counting how many times they appeared in the map step. The reducer layer then aggregates the values in the list and saves them. Then the final output is saved in an output file. The advantage of MapReduce is its ability to allow for a high level of parallel jobs across multiple nodes. A node is an independent computer used for processing and storing big volumes of data. In Hadoop, we have 2 types of nodes, the name node and the data node. MapReduce allows for splitting and running independent tasks in parallel by dividing each task, which in turn saves time. MapReduce is very flexible and can produce data that come in tabular and non-tabular forms. Therefore, MapReduce provides business value to organizations regardless of how their data is structured. It also offers support for different languages and provides a platform for analysis, data warehousing, and more. MapReduce has a couple of use cases, and here we have some of them displayed. MapReduce can be used for social media platforms like LinkedIn and Instagram to analyze who visited, viewed, and interacted with your profile posts. MapReduce is used by Netflix to recommend movies based on what you have watched in the past by using the user's interest. It is also used in financial institutions like banks and credit card companies to flag and detect anomalies in user transactions. It can also be used in the advertisement industry to understand a user's behavior by how they engage with ads. Google Ads work by using MapReduce to understand the engagement of users with an ad. In this video, you have learned that MapReduce is a framework used in parallel computing. It contains two major tasks, map and reduce. Map processes data into key value pairs, sorts and organizes the data. The reducer aggregates and computes a set of results and produces a final output. It is flexible for all data types like structured and unstructured data, and can be applied to multiple industries such as social media, entertainment, and many more. Welcome to Introduction to MapReduce. After watching this video, you'll be able to explain the terms map and reduce in MapReduce, describe why we use MapReduce, list the components of MapReduce, outline examples of common use cases of MapReduce. What is MapReduce? MapReduce is a programming model that enables massive scalability across hundreds or thousands of servers in a Hadoop cluster. As the processing component, MapReduce is the heart of Apache Hadoop. MapReduce is a processing technique and a program model for distributed computing. It is based on Java. Distributed computing is a system or machine with multiple components located on different machines. Each component has its own job, but the components communicate with each other to run on one system to the end user. The MapReduce algorithm consists of two important tasks, map and reduce. Many MapReduce programs are written in Java. MapReduce can also be coded in C++, Python, Ruby, R, and so on. As the name suggests, the MapReduce framework contains two tasks, map and reduce. Map takes in an input file and performs some mapping tasks by processing and extracting important data information into key value pairs, and these are the preliminary output list. Some more reorganization goes on before the preliminary output is sent to the reducer. The reducer works with multiple map functions and aggregates the pairs using their keys to produce a final output. MapReduce keeps track of its tasks by creating unique keys to ensure that all the processes are solving the same problem. Let's look at the framework visually. First, we have the map step, which takes a set of data and converts it into another set of data, where individual elements are broken down into key value pairs. The key is the name, and the value is the content. The input data is a file that is saved in the Hadoop file system called HDFS. Now let's assume we have an input file that contains names of people, and we would like to do a word count on the unique name occurrences. First, the data is split into the following 4 files, each of them in key value pairs and are worked on separately. For example, for the first split line for Teju and Brianna, we have 2 key value pairs with 1 occurrence in each file, and it will do the same for all key value pairs. We then have the reducer. The reducer processes the data that comes from the map. After processing, it produces a new set of outputs, which will be stored in the HDFS. The reducer starts with shuffling. Shuffling sorts the key and a list of values in a list. For example, you will see the key Teju and a corresponding list of values from the previous step. We will have Teju 111. This is because the name Teju occurred 3 times in the map step. It does the same for the rest of the names, counting how many times they appeared in the map step. The reducer layer then aggregates the values in the list and saves them. Then the final output is saved in an output file. The advantage of MapReduce is its ability to allow for a high level of parallel jobs across multiple nodes. A node is an independent computer used for processing and storing big volumes of data. In Hadoop, we have 2 types of nodes, the name node and the data node. MapReduce allows for splitting and running independent tasks in parallel by dividing each task, which in turn saves time. MapReduce is very flexible and can produce data that come in tabular and non-tabular forms. Therefore, MapReduce provides business value to organizations regardless of how their data is structured. It also offers support for different languages and provides a platform for analysis, data warehousing, and more. MapReduce has a couple of use cases, and here we have some of them displayed. MapReduce can be used for social media platforms like LinkedIn and Instagram to analyze who visited, viewed, and interacted with your profile posts. MapReduce is used by Netflix to recommend movies based on what you have watched in the past by using the user's interest. It is also used in financial institutions like banks and credit card companies to flag and detect anomalies in user transactions. It can also be used in the advertisement industry to understand a user's behavior by how they engage with ads. Google Ads work by using MapReduce to understand the engagement of users with an ad. In this video, you have learned that MapReduce is a framework used in parallel computing. It contains two major tasks, map and reduce. Map processes data into key value pairs, sorts and organizes the data. The reducer aggregates and computes a set of results and produces a final output. It is flexible for all data types like structured and unstructured data, and can be applied to multiple industries such as social media, entertainment, and many more. Welcome to Hadoop ecosystem. After watching this video, you'll be able to list the stages of the Hadoop ecosystem, differentiate between the core components and the extended components, list some examples of tools used in each stage. Apart from the core components of Hadoop, Hadoop Common refers to the common utilities and libraries that support the other Hadoop modules. Hadoop Distributed File System, HDFS, stores the data collected from the ingestion and distributes the data across multiple nodes. MapReduce is used for making big data manageable by processing them in clusters. Yet another resource negotiator, Yarn, is the resource manager across clusters. The extended Hadoop ecosystem consists of libraries or software packages that are commonly used with or installed on top of the Hadoop core. The Hadoop ecosystem is made of components that support one another for big data processing. We can examine the Hadoop ecosystem based on the various stages. When data is received from multiple sources, Flume and Scoop are responsible for ingesting the data and transferring them to the storage component HDFS and HBase. Then, the data is distributed to a MapReduce framework like Pig and Hive to process and analyze the data, and the processing is done by parallel computing. After all that is done, tools like Hue are used to access the refined data. Ingesting is the first stage of big data processing. Whenever you deal with big data, you get data from different sources. You then use tools like Flume and Scoop. Flume is a distributed service that collects, aggregates, and transfers big data to the storage system. Flume has a simple and flexible architecture based on streaming data flows and uses a simple, extensible data model that allows for online analytic application. Scoop is an open-source product designed to transfer bulk data between relational database systems and Hadoop. Scoop looks in the relational database and summarizes the schema. It then generates MapReduce code to import and export data as needed. Scoop allows you to quickly develop any other MapReduce applications that use the records that Scoop stored into HDFS. HBase is a column-oriented, non-relational database system that runs on top of HDFS. It provides real-time wrangling access to the Hadoop file system. HBase uses hash tables to store data in indexes and allow for random access of data, which makes lookups faster. Cassandra is a scalable NoSQL database designed to have no single point of failure. In the Analyze Data stage, Pig is used for analyzing large amounts of data. Pig is a procedural data flow language and a procedural programming language that follows an order and set of commands. Hive is used mainly for creating reports and operates on the server side of a cluster. Hive is a declarative programming language, which means it allows users to express which data they wish to receive. The final stage is Access Data, where users have access to the analyzed and refined data. At this stage, tools like Impala are often used. Impala is a scalable system that allows non-technical users to search and access the data in Hadoop. You do not need to be skilled in programming to use Impala. And Hue is another tool of choice at this stage. Hue is an acronym for Hadoop User Experience. Hue allows you to upload, browse, and query data. You can run pig jobs and workflow in Hue. Hue also provides a SQL editor for several query languages like Hive and MySQL. In this video, you learned that the 4 main stages of the Hadoop ecosystem are ingest, store, process and analyze, and access. Some examples of the tools associated with each stage, and how each stage interacts with the others. Welcome to Hadoop Distributed File System. After watching this video, you'll be able to explain Hadoop Distributed File System and important concepts, identify the key HDFS features, describe the HDFS architecture. HDFS stands for Hadoop Distributed File System. A distributed file system is a file system that is distributed on multiple file servers and allows programmers to access or store files from any network or computer. HDFS is the storage layer of Hadoop. HDFS works by splitting the files into blocks, then creating replicas of the blocks and storing them on different machines. HDFS is built to access streaming data seamlessly. Streaming means that HDFS provides a constant bit rate when transferring data, rather than having the data being transferred in waves. HDFS uses a command line interface to interact with Hadoop. The key features of HDFS are: the commodity hardware that stores the data is not expensive and therefore reduces storage costs. HDFS can store very large amounts of data, as large as petabytes, in any format, tabular and non-tabular. It splits these large amounts of data into small chunks called blocks. One of the great features of HDFS is its ability to replicate and minimize the costs associated with data losses when there is failure with one of the hardware units. That capability makes HDFS fault-tolerant. In the event of a data loss of one of the computers, the data can be found on another computer and work continues. HDFS is also highly scalable. A single cluster can scale into hundreds of nodes. Portability is also one of the key features, as HDFS is designed to easily move from one platform to another. To get familiar with Hadoop, there are a few concepts to know. When HDFS receives files, files are broken into smaller chunks called blocks. A block is the minimum amount of data that can be read or written and provides fault tolerance. Depending on your system configuration, the default block size could be 64 or 128 megabytes. For example, if we had a 500 megabyte file with a default block chunk size of 128 megabytes, the file will be divided into 3 blocks of 128 megabytes and 1 block of 116 megabytes. The only time you will have equal splits is if the file size is a multiple of the default block size. Therefore, you can see that each file stored doesn't have to take up the storage of the pre-configured block size. Let's start with nodes. A node is a single system which is responsible for storing and processing data. Think about it as one machine or computer in which data is stored. Remember that HDFS follows the primary-secondary concept. HDFS has 2 types of nodes. The primary node, known as the name node, regulates file access to the clients and maintains, manages, and assigns tasks to the secondary node, also known as a data node. There can be hundreds of data nodes in the HDFS that manage the storage system. They perform read and write requests at the instruction of the name node. When performing operations like read and write, it is important that the name node maximizes performance by choosing the data nodes closest to themselves. This could be by choosing data nodes on the same rack or in nearby racks. This is called rack awareness. A rack is the collection of about 40 to 50 data nodes using the same network switch. Rack awareness is used to reduce the network traffic and improve cluster performance. To achieve rack awareness, the name node keeps the rack ID information. Replication is done by rack awareness as well. It is done by making sure replicas of a data node are in different racks. So, if a rack is down, you can still obtain the data from another rack. HDFS is known for optimizing replication. HDFS uses the rack awareness concept to create replicas to make sure that the data is reliable and available, and that the network bandwidth is properly utilized. Replication is creating a copy of the data block. When crashes happen, replication provides backup of the data blocks. Replication factor is defined as the number of times you make a copy of the data block. Depending on your configuration, you can set the number of copies you want. Let's look at our 500 megabyte file example. If our replication factor is 2, it will create 2 copies of each block. That means we will have 4 times 2, which is 8 copies of the file blocks for backup. HDFS uses the rack awareness concept and saves the blocks in different racks to make sure that a copy is available in another rack. For example, you could have 4 racks of 2 copies each. If one of the racks is down or crashes, you will still have a copy of the data blocks in a different rack, and you can still work with the data. Another important concept is how read and write operations are performed in HDFS. HDFS allows write once, read many operations. This means that you cannot edit files that are already stored in HDFS, but you can append new data to them. Let's start with how the read operation works. Assuming we have a text file, the client will send a request to the primary node, which is the name node, to get the location of the data nodes containing blocks. The name node will verify that the client has the correct privileges and provide the client with the locations. A client in HDFS interacts with the primary and secondary nodes to fulfill a user's request. The client will then send a request to the closest data nodes through an FS data input stream object by calling the read method to read all the files. And when the client is done, the client will use the close method to end the session. Next, we will see how the write operation works. Just like in the read operation, the name node confirms that the client has the right privileges. The name node makes sure to check that the file doesn't exist in the system. If the file already exists, the client will receive an I/O exception. If the file doesn't exist, the client receives a write permission together with the data nodes. Once the client is done, the data nodes start creating replicas and sends a confirmation to the client. Hadoop follows the concept of a primary-secondary node architecture. The primary node is the name node. The architecture is such that per cluster, there is one name node and multiple data nodes, which are the secondary nodes. Internally, a file is split into one or more blocks, and these blocks are stored in a set of data nodes. The name node oversees opening, closing, renaming file operations, and mapping file blocks to the data node. The data nodes are responsible for read and write requests from the client and perform the creation, replication, and deletion of file blocks based on instructions from the name node. In this video, you learned that key HDFS benefits include its cost efficiency, scalability, data storage expansion, and data replication capabilities. A block is the minimum size of a file. Replication creates a copy of data blocks for backup purposes. Rack awareness helps reduce the network traffic and improve cluster performance. HDFS enables write once, read many operations. Welcome to Hive. After watching this video, you'll be able to articulate the reasons why Hive is used, list Hive features, differentiate between Hive and traditional RDBMS, identify components of the Hive architecture, discuss Hive concepts. Hive is a data warehouse software within Hadoop that is designed to read, write, and manage large and tabular type datasets and data analysis. A data warehouse stores historical data from many different sources so that you can analyze and extract insights from it. These insights are used for reporting. Hive is scalable and fast because it is designed to work on petabytes of data. Hive is easy to use if you are familiar with SQL because Hive Query Language or HiveQL is based on SQL. This makes learning quicker because users who already deal with relational databases can easily grasp the concepts. Hive supports the following file formats: sequence files consisting of binary key-value pairs, record columnar files that store columns of a table in a columnar database, and text or flat files. Hive allows for data cleaning and filtering tasks according to users' requirements. RDBMS is a type of database management system specifically designed for relational databases. RDBMS is the acronym for Relational Database Management System. A relational database is a database that stores data in a structured format using rows and columns known as a table. Let's look at the differences between a traditional RDBMS and Hive. Traditional RDBMS is used to maintain a database and uses the structured query language known as SQL. Hive is used to maintain a data warehouse and uses the Hive query language, a language inspired by SQL. Traditional RDBMS is suited for real-time data analysis, like data from sensors. Hive is suited for static data analysis. Traditional RDBMS allows for as many read and write operations a user needs. Hive is based on the write once, read many methodology. Traditional RDBMS can handle up to terabytes of data. Hive is designed to handle as much as petabytes of data. Another difference is that traditional RDBMS enforces that the schema must verify loading data before it can proceed. Hive doesn't enforce the schema to verify loading data. Lastly, traditional RDBMS may not always have built-in for support data partitioning. Hive supports partitioning. Partitioning means dividing the table into parts based on the values of a particular column, such as a date or city. This is what Hive architecture looks like. There are three main parts of the architecture. The Hive client. Hive provides different drivers for communication depending on the type of application. For example, for Java-based applications, Hive uses JDBC drivers, and other types of applications will use ODBC drivers. These drivers communicate with the servers. Hive services. Client interactions are done through the Hive services. Any query operations are done here. The command line interface acts as an interface for the Hive service. The driver takes in query statements, monitors the progress and life cycle of each session, and stores metadata generated from the query statements. The metastore stores the metadata, the data and information about each table, such as the location and schema. The metastore, file system, and job client in turn communicate with Hive storage and computing to perform the following. Metadata information of tables are stored in some sort of database and query results, and data loaded in the tables are stored in Hadoop cluster or HDFS. Let's look at the concepts in detail. Components in the Hive clients include the JDBC client, which allows Java-based applications to connect to Hive, and the ODBC client, which allows applications based on the ODBC protocol to connect to Hive. The Hive Services section of the architecture is in charge of performing queries. The Hive server is used to run queries and allows multiple clients to submit requests. It is built to support the JDBC and ODBC clients. The driver receives query statements submitted through the command line and sends the query to the compiler after initiating a session. The optimizer performs transformations on the execution plan and splits the tasks to help speed up and improve efficiency. The executor executes tasks after the optimizer has split the tasks. The metastore is storage for the metadata, which is information about the table. The metastore is in charge of keeping this information in a central place. In this video, you learned that Hive is a data warehouse software for reading, writing, and managing data sets. Although Hive works very similarly to traditional RDBMS, they are slightly different. The three main parts of the Hive architecture are Hive Client, Hive Services, and Hive Storage and Computing. Welcome to HBase. After watching this video, you'll be able to define HBase, describe HBase as a columnar database, list the HBase features and usage, outline the differences between HBase and HDFS, describe the HBase architecture, discuss HBase concepts. HBase is a column-oriented non-relational database management system that runs on top of Hadoop Distributed File System, or HDFS. It provides a fault-tolerant way of storing sparse data sets. Fault tolerance refers to the working ability of a system or computer to continue working even in unfavorable conditions, such as when a server crashes. It works well with real-time data and random read and write access to big data. HBase is used for write-heavy applications to store large amounts of data sets and process and provide analytics in real time. It is referred to as linearly scalable because it supports scalability in both linear and modular form. HBase is a backup support for MapReduce jobs. HBase can be used for high-speed requirements because it offers consistent reads and writes. HBase has no fixed columns and is only defined by column families. It provides an easy-to-use Java API for client access. HBase supports data replication across clusters. An HBase column represents an attribute of an object. Let's look at an example. If the table is storing sensors from heart monitors in the hospital, each row might be a log record. A typical column could contain information about the patient's details or the time when the log record was taken. HBase allows for many attributes to be grouped together into column families, such that the elements of a column family are all stored together. For example, patient name and patient age will be stored as patient details. The columns in HBase will look like patient details, heart rate, and timestamp. When creating schemas in HBase, you must predefine the table schema and specify the column families. New columns can be added to families at any time, making the schema flexible and adaptable to changing application requirements. Just as HDFS has a name node and secondary nodes, HBase is built on similar concepts. In HBase, a primary node manages the cluster, and a region server stores portions of the tables and performs the work on the data. While HBase and HDFS are both used to store massive amounts of data, one of the major differences is that HBase stores data in the form of columns and rows in a table, while HDFS stores in a distributed manner across different nodes on that network. HBase allows dynamic changes, while HDFS has a rigid architecture that doesn't allow changes. HBase is suitable for read, write, update, and delete type workloads on a record level. HDFS is just an underlying level resembling properties of a file system, so is more suited for write once and read in batch workloads. HBase allows for storing and processing of big data, while HDFS is for storing only. The HBase architecture consists mainly of 4 components. 1. HMaster. 2. HRegion server. 3. HRegions. 4. Zookeeper. From the architecture, we can see that HBase sits and works on top of HDFS. HDFS provides a distributed environment for the storage, and it is a file system designed to run on commodity hardware. It stores each file in multiple blocks, and to maintain fault tolerance, it replicates the blocks across a Hadoop cluster. HMaster is a master server. It monitors the region server instances, assigns regions to region servers, and distributes services to different region servers, and manages any changes that are made to the schema and metadata operations. The region servers receive read and write requests from the client and assign the request to a specific region where the column family resides. They are responsible for serving and managing regions that are present in a distributed cluster. Rather than go through HMaster all the time, the region servers can communicate directly with the client to facilitate requests. The region is the basic building element and smallest unit of the HBase cluster that consists of column families. It contains multiple stores, one for each column family, and has 2 components, HFile and memstore. Zookeeper is a centralized service for maintaining configuration information to maintain healthy links between nodes. It provides synchronization across distributed applications and is used to track server failure and network partitions by triggering an error message and then starts repairing the failed nodes. In this video, you learned that HBase is a column-oriented non-relational database management system that runs on HDFS. HBase columns are defined by column families. HBase is linearly scalable, highly efficient, and provides an easy-to-use Java API for client access. A key difference between HDFS and HBase is that HBase allows dynamic changes compared to the rigid architecture of HDFS. HBase architecture consists of HMaster, region servers, region, Zookeeper, and HDFS. Welcome to Why Use Apache Spark. After watching this video, you'll be able to describe Apache Spark attributes, describe distributed computing, list the benefits of Apache Spark and distributed computing, compare and contrast Apache Spark to MapReduce. Spark is an open-source, in-memory application framework for distributed data processing and iterative analysis on massive data volumes. Let's review the key words in this sentence. First, Spark is entirely open source. Spark is available under the Apache Foundation, hence the name Apache Spark. Next, Spark is in-memory, which means that all operations happen within the memory or RAM. Distributed data processing uses Spark. Finally, Spark scales very well with data, which is ideal for massive data sets. Spark is primarily written in Scala, a general-purpose programming language that supports both object-oriented and functional programming. Spark runs on Java virtual machines. Distributed computing, as the name suggests, is a group of computers or processors working together behind the scenes. People often use the terms distributed computing and parallel computing interchangeably, as the two computing types have many similarities. However, distributed computing and parallel computing access memory differently. Typically, parallel computing shares all the memory, while in distributed computing, each processor accesses its own memory. Let's look at two top distributed computing benefits. First, distributed computing offers scalability and modular growth. Distributed systems are inherently scalable as they work across multiple machines and scale horizontally. A user can add additional machines to handle the increasing workload instead of repeatedly updating a single system with virtually no cap for scalability. Second, distributed systems require both fault tolerance and redundancy, as they use independent nodes that could fail. Distributed computing offers more than fault tolerance. Distributed computing provides redundancy that enables business continuity. For example, a business running a cluster of 8 machines can continue to function whether a single machine or multiple machines go offline. Spark checks the boxes for all the benefits of distributed computing. Spark supports a computing framework for large-scale data processing and analysis. Spark also provides parallel distributed data processing capabilities, scalability, and fault tolerance on commodity hardware. Spark provides in-memory processing and creates a comprehensive, unified framework to manage big data processing. Spark enables programming flexibility with easy-to-use Python, Scala, and Java APIs. How does Apache Spark compare to more traditional big data tools like MapReduce? A traditional MapReduce job creates iterations that require reads and writes to disk or HDFS. These reads and writes are usually time-consuming and expensive. Apache Spark solves the read-write problems encountered with MapReduce by keeping much of the data required in memory and avoiding expensive disk I/O, thus reducing the overall time by orders of magnitude. Spark provides big data solutions for both data engineering problems and data science challenges. Data engineers use Spark tools, including the core Spark engine, clusters and executors and their management, Spark SQL, and data frames. Additionally, Spark also supports data science and machine learning through libraries such as Spark ML and streaming. In this video, you learned that Spark is an open-source in-memory application framework for distributed data processing and iterative analysis on massive data volumes. Distributed computing is a group of computers or processors working together behind the scenes. Both distributed systems and Apache Spark are inherently scalable and fault-tolerant. Apache Spark keeps a large portion of the data required in memory and avoids expensive and time-consuming disk I/O. Welcome to Functional Programming Basics. After watching this video, you'll be able to explain the term functional programming, explain lambda functions, relate functional programming with Apache Spark. So, what is functional programming? Functional programming, or FP, is a style of programming that follows the mathematical function format. Think of an algebra class with the f of x notation. The notation is declarative in nature as opposed to being imperative. By declarative, we mean that the emphasis of the code or program is on the what of the solution as opposed to the how-to of the solution. Declarative syntax abstracts out the implementation details and only emphasizes on the final output, restated, the what. We use expressions in functional programming like the expression f of x as mentioned earlier. Historically, LIST processing language, known as Lisp, was the first functional programming language starting in the 1950s. But today, there are many functional programming language options, including Scala, Python, R, and Java. Scala is the most recent representative in this family of programming languages. Apache Spark is written mainly in Scala, which treats functions as first-class citizens. Functions in Scala can be passed as arguments to other functions, returned by other functions, and used as variables. Here is a simple example of a functional program that increments a number by 1. We define the function f of x equal x plus 1. We can then apply this function to a list of size 4, as shown in the figure, and the program increments every element in the list by 1. That's the advantage of using functional programming. You can directly apply functions to an entire list or array. If you perform the same task in an imperative paradigm using procedural code, you will construct a for loop that iterates over the array and increment each element by 1. This programming paradigm differs from the preceding example by explicitly listing all the steps to be performed, including the go-over for each element, incrementing each element by 1. This code places emphasis on the how-to. Compare and contrast this traditional programming example to the functional programming example that emphasized on the what part of the solution. Parallelization is one of the main benefits of functional programming. Consider the previous example where the program incremented by 1 up to 4. Here is a larger array, from 1 to 9. You can split the task into 3 different computing chunks, which can be referred to as nodes. Click 1 and run those 3 tasks or nodes in parallel. This method's beauty is that you do not need to change any of the function definitions or the code. All you need to do is run more than one instance of the task in parallel. By applying implicit parallelization functional programming capabilities, you can scale the algorithm to any size by adding more compute and resources without modifying the program or code. The result is the same as if the function exists on only a single node. However, in this case, the function ran 3 times in parallel without requiring any changes to the function or code. Functional programming applies a mathematical concept called lambda calculus. To keep the explanation simple, lambda calculus basically says that every computation can be expressed as an anonymous function which is applied to a data set. Lambda functions or operators are anonymous functions used to write functional programming code. Here, we have the code written in functional programming style using lambda functions and operators and add 2 numbers using 2 popular languages, Scala, as seen on the left, and Python, as seen on the right. Note how both codes are similar in flow and abstract out the result directly, a hallmark of the declarative paradigm of programming. Apache Spark is capable of quickly working through big data by lambda functions distributing work between worker nodes and parallelized computations. All Spark programs implemented this way are inherently parallel, so it doesn't matter if you analyze 1 kilobyte or 1 petabyte of data. Just add additional resources to the Spark cluster, and you're done. In this video, you learned that functional programming follows a declarative programming model that emphasizes what instead of how to and uses expressions. Lambda functions or operators are anonymous functions that enable functional programming. Spark parallelizes computations using the lambda calculus. All functional Spark programs are inherently parallel. Welcome to parallel programming using resilient distributed data sets. After watching this video, you'll be able to define resilient distributed data sets referred to as RDDs, define parallel programming, explain resilience in Apache Spark, relate RDD and parallel programming with Apache Spark. A resilient distributed data set, also known as an RDD, is Spark's primary data abstraction. A resilient distributed data set is a collection of fault-tolerant elements partitioned across the cluster's nodes capable of receiving parallel operations. Additionally, resilient distributed databases are immutable, meaning that these databases cannot be changed once created. Every Spark application consists of a driver program that runs the user's main functions and runs multiple parallel operations on a cluster. RDDs support text, sequence files, Avro, Parquet, and Hadoop input format file types. RDDs also support local, Cassandra, HBase, HDFS, Amazon S3, and other file formats, in addition to an abundance of relational and NoSQL databases. First, you can create an RDD using an external or local file from a Hadoop-supported file system, such as HDFS, Cassandra, HBase, or Amazon S3. A second method is to apply the parallelize function to an existing collection in the driver program. Note that this driver program can be in any of the supported high-level APIs, including Python, Java, and Scala. This simple code snippet, shown on screen using both Scala and Python, creates an RDD from an existing collection. In this case, we use a list. You'll see SC applied to the snippet. One important parameter for parallel collections is the number of partitions specified to cut the dataset. Spark runs one task for each partition of the cluster. Typically, you want 2 to 4 partitions for each CPU in your cluster. Spark tries to automatically set the number of partitions based on your cluster. However, you can also set partitions manually by passing the number as a second parameter to the parallelize function. A third method of creating an RDD in Spark is to apply a transformation on an existing RDD to create a new RDD. Next, let's define parallel programming. Parallel programming, like distributed programming, is the simultaneous use of multiple compute resources to solve a computational task. Parallel programming parses tasks into discrete parts that are solved concurrently using multiple processors. The processors access a shared pool of memory, which has in place control and coordination mechanisms. Here is an example of how RDDs enable parallel programming. This example is similar to creating an RDD in Spark. You create an RDD by parallelizing an array of objects or by splitting a dataset into partitions. Nodes receive the distributed partitions. Spark runs one task for each partition of the cluster. Based on how RDDs are created, RDDs can inherently be operated on in parallel. So, how do RDDs provide resilience in Spark? RDDs provide resilience in Spark through immutability and caching. First, RDDs are always recoverable as the data is immutable. Another essential Spark capability is the persisting or caching of a dataset in memory across operations. The cache is fault-tolerant and always recoverable, as RDDs are immutable, and the Hadoop data source is also fault-tolerant. When you persist an RDD, each node stores the partitions that the node computed in memory and reuses the same partition in other actions on that dataset or the subsequent datasets derived from the first RDD. Persistence allows future actions to be much faster, often by more than 10 times. Persisting, or caching, is used as a key tool for iterative algorithms and fast, interactive use. In this video, you learned that you can create an RDD using an external or local file from a Hadoop-supported file, a collection, or another RDD. RDDs are immutable and always recoverable. Parallel programming is the simultaneous use of multiple compute resources to solve a computational task. RDDs can persist or cache datasets in memory across operations, which speeds iterative operations. Welcome to Scale Out and Data Parallelism in Apache Spark. After watching this video, you'll be able to describe Apache Spark components. Describe how Apache Spark scales with big data. Apache Spark architecture consists of three main components. The first component is data storage. Datasets load from data storage into memory. Any Hadoop-compatible data source is acceptable. High-level programming APIs comprise the second component. Spark has APIs in Scala, Python, and Java. The final component is the cluster management framework, which handles the distributed computing aspects of Spark. Spark's cluster management framework can exist as a standalone server, Mesos, or yet another resource network, or YARN. A cluster management framework is essential for scaling big data. Here is a simple visualization of the three pieces. The data from a Hadoop file system flows into the compute interface, or API, which then flows into different nodes to perform distributed parallel tasks. What is often referred to as Spark is the base engine formerly called the Spark core. The fault-tolerant Spark core is the base engine for large-scale parallel and distributed data processing. Spark core manages memory and task scheduling. Spark core also contains the APIs used to define RDDs and other data types. Spark core also parallelizes a distributed collection of elements across the cluster. To understand how Spark scales with big data, let's review the Spark application architecture. The Spark application consists of the driver program and the executor program. Executor programs run on worker nodes. Spark can start additional executor processes on a worker if there is enough memory and cores available. Similarly, executors can also take multiple cores for multi-threaded calculations. Spark distributes RDDs among executors. Communication occurs among the driver and the executors. The driver contains the Spark jobs that the application needs to run and splits the jobs into tasks submitted to the executors. The driver receives the task results when the executors complete the tasks. If Apache Spark were a large organization or company, the driver code would be the executive management of that company that makes decisions about allocating work, obtaining capital, and more. The junior employees are the executors who do the jobs assigned to them with the resources provided. The worker nodes correspond to the physical office space that the employees occupy. You can add additional worker nodes to scale big data processing incrementally. In this video, you learned that Apache Spark architecture consists of three main pieces: components, data, compute input, and management. The fault-tolerant Spark Core base engine performs large-scale parallel and distributed data processing, manages memory, schedules tasks, and houses APIs that define RDDs. The Spark driver program communicates with the cluster and then distributes RDDs among worker nodes. Welcome to Spark SQL and data frames. After watching this video, you'll be able to define Spark SQL, define the parts of a Spark SQL query, and explain the benefits of using Spark SQL. Describe what data frames are, define the parts of a data frame query, and explain the benefits of using a data frame. Explain how data frames work with Spark SQL. Spark SQL is a Spark module for structured data processing. You can interact with Spark SQL using SQL queries and the data frame API. Spark SQL supports Java, Scala, Python, and R APIs. Spark SQL uses the same execution engine to compute the result independently of which API or language you are using for the computation. Developers can use the API that provides the most natural way to express a given transformation. Here is an example of a Spark SQL query using Python. The query, select star from people statement, is the SQL query run using Spark SQL. The entity people was registered as a table view before this command. Unlike the basic Spark RDD API, Spark SQL includes a cost-based optimizer, columnar storage, and code generation to perform optimizations that provide Spark with additional information about the structure of both the data and the computation in process. So, what is a data frame? A data frame is a collection of data organized into named columns. Data frames are conceptually equivalent to a table in a relational database and similar to a data frame in R Python, but with richer optimizations. Data frames are built on top of the Spark SQL RDD API. Data frames use RDDs to perform relational queries. Here is a simple code snippet in Python to read from a JSON file and create a simple data frame. The last step of registering the data frames runs SQL queries on this data using Spark SQL. Here you see the input data file in JSON format and the resulting data frame. Data frames offer many benefits. Data frames are highly scalable, from a few kilobytes on a single laptop to petabytes on a larger cluster of machines. Data frames support a wide array of data formats and storage systems. Data frames provide optimization and code generation through a Catalyst optimizer. Last, data frames are developer-friendly, offering integration with most big data tooling via Spark and APIs for Python, Java, Scala, and R. These code snippets show how to run the same SQL query and the result of those queries using Spark SQL. All three queries shown here achieve the same result of showing the names column from our data frame. The first query is a more traditional SQL query, while the other two code examples use the data frame Python API to perform the same task. Similarly, here are two different ways to query the entries in the data frame to locate people who are above the age of 21. The first code example is a SQL query, while the second code example uses the data frame API. In this video, you learned that Spark SQL is a Spark module for structured data processing. Spark SQL provides a programming abstraction called data frames and can also act as a distributed SQL query engine. Data frames are conceptually equivalent to a table in a relational database or a data frame in R Python, but with richer optimizations. Welcome to Resilient Distributed Datasets in Parallel Programming and Spark. After watching this video, you'll be able to describe resilient distributed datasets, explain how to use resilient distributed datasets in Spark, explain RDD transformation and actions, and list fundamental transformations and actions. Resilient distributed datasets, known as RDDs, are Spark's primary data abstraction and are partitioned across a cluster's nodes. The first RDD operation to explore is a transformation. An RDD transformation creates a new RDD from an existing RDD. Transformations in Spark are considered lazy because Spark does not compute transformation results immediately. Instead, the results are only computed when evaluated by actions. For example, the map transformation passes each element of a dataset through a function, resulting in a new RDD. To evaluate a transformation in Spark, you use an action. The action returns a value to the driver program after running a computation. One example is the reduce action, which aggregates all the elements of an RDD and returns the result to the driver program. But how do transformations and actions happen? Spark uses a unique data structure called a directed acyclic graph, known as a DAG, and an associated DAG scheduler to perform RDD operations. Think of a DAG as a graphical structure composed of edges and vertices. The term acyclic means new edges only originate from an existing vertex. In general, the vertices and edges are sequential. The vertices represent RDDs and the edges represent the transformations or actions. The DAG scheduler applies the graphical structure to run the tasks that use the RDD to perform transformation processes. So why does Spark use DAGs? DAGs help enable fault tolerance. When a node goes down, Spark replicates the DAG and restores the node. Let's look at the process in more detail. First, Spark creates DAG when creating an RDD. Next, Spark enables the DAG scheduler to perform a transformation and updates the DAG. The DAG now points to the new RDD. The pointer that transforms RDD is returned to the Spark driver program. And if there is an action, the driver program that calls the action evaluates the DAG only after Spark completes the action. Here are some examples of RDD transformations and actions. We have already mentioned map, which is an essential operation and capable of expressing all transformations needed in data science. Some of the more common high-level transformations making use of map and reduce include filter, which enables filtering the elements of a dataset based on a function, and distinct, which finds the number of distinct elements in a dataset. In addition, the flat map transformation, which is similar to the map transformation, can map each input item to 0 or greater output items. Its function should return a sequence rather than a single item. Next, frequently used actions include reduce, which aggregates dataset elements using the function. Take, which returns an array with the first n element. Collect, which returns all the elements of the dataset as an array. And take ordered, which returns elements ordered in ascending order or as specified by an optional function argument. You can find more details about transformations and actions on the spark.apache.org website. A transformation is only a mapping of operations. You need actions to get the computed values to the driver program. This example considers a function f of x that decrements x by 1. So, f of x equals x minus 1. You'll apply this function as a transformation to a dataset using the map transformation. Each task makes a new partition by calling f of e on each entry e in the original partition. Then, the collect action gathers the entries from all the partitions into the driver, which receives the results. In this video, you learned that RDDs are Spark's primary data abstraction partitioned across the nodes of the cluster. Spark uses DAGs to enable fault tolerance. When a node goes down, Spark replicates the DAG and restores the node. Transformations leave existing RDDs intact and create new RDDs based on the transformation function. Transformations undergo lazy evaluation, meaning they are only evaluated when the driver function calls an action. Welcome to Datasets and Data Frames in Spark. After watching this video, you'll be able to describe dataset features and benefits within Apache Spark. Explain 3 ways you can create datasets for use in Spark. Summarize the differences between datasets and data frames. Datasets are the newest Spark data abstraction. Like RDDs and data frames, datasets provide an API to access a distributed data collection. Datasets are a collection of strongly typed Java Virtual Machine, or JVM, objects. Strongly typed means that datasets are type-safe, and the dataset's data type is made explicit during its creation. Datasets provide the benefits of both RDDs, such as Lambda functions, type safety, and SQL optimizations from Spark SQL. Speaking of benefits, here are 4 more features of datasets. Datasets are immutable. Like RDDs, they cannot be deleted or lost. Datasets feature an encoder that converts type-specified JVM objects to a tabular representation. Datasets extend the data frame API. Conceptually, a dataset of a generic untyped row is a JVM object seen as a column of a data frame. Because datasets are strongly typed, APIs are currently only available in Scala and Java, which are statically typed languages. Dynamically typed languages, such as Python and R, do not support dataset APIs. Datasets offer some unique advantages and benefits over using data frames and RDDs. Because datasets are statically typed, datasets provide compile-time type safety. Compile-time type safety means that Spark can detect syntax and semantic errors in production applications before deployment, saving substantial developer and operational costs and time. Datasets compute faster than RDDs, especially for aggregate queries. Datasets offer the additional query optimization enabled by Catalyst and Tungsten. Datasets enable improved memory usage and caching. But how? Spark understands the data structure of the datasets and optimizes the layout within memory. The Dataset API also offers functions for convenient, high-level aggregate operations, including sum, average, join, and group by. Let's now look at 3 ways that you can create a dataset within Spark. This first example, written in Scala, uses the toDs function to create a dataset from a sequence. This second example illustrates how to create a dataset from a text file. Notice the explicit schema declaration. In this example, we apply the primitive string data type to the explicit schema declaration. This third and final example creates a dataset using a JSON file. In this last example, we use a custom class called Customer, which contains a name and an ID field. Next, let's compare datasets to data frames. Datasets offer the benefits of both its predecessors, data frames and RDDs. Datasets are strongly typed. Data frames are not type-safe. Datasets can use unified Java and Scala APIs. Data frames use APIs that are written in Java, Scala, Python, and R. The data frames API may or may not be unified depending on the API version. Datasets are the latest addition to Spark and are built on top of data frames. In contrast, data frames introduced earlier are built on RDDs. In this video, you learned that A dataset is a distributed collection of data that provides the combined benefits of both RDDs and Spark SQL. Datasets consist of strongly typed JVM objects. Datasets use data frame type-safe capabilities and extend object-oriented API capabilities. Datasets work with both Scala and Java APIs. Welcome to Spark SQL memory optimization using Catalyst and Tungsten. After watching this video, you'll be able to describe the goals of Apache Spark SQL optimization, describe how Catalyst and Tungsten benefit Spark SQL, explain how Spark performs SQL and memory optimization using Catalyst and Tungsten. The primary goal of Spark SQL optimization is to improve the SQL query runtime performance, reducing the query's time and memory consumption, saving organizations time and money. Spark SQL supports both rule-based and cost-based query optimization. Catalyst, also known as the Catalyst Optimizer, is the Spark SQL built-in rule-based query optimizer. Based on Scala functional programming constructs, Catalyst is designed to easily add new optimization techniques and features to Spark SQL. Developers can extend the optimizer by adding data source-specific rules and support for new data types. During rule-based optimization, the SQL optimizer follows predefined rules that determine how to run the SQL query. Examples of predefined rules include validating that a table is indexed and checking that a query contains only the required columns. With the query itself optimized, cost-based optimization measures and calculates cost based on the time and memory that the query consumes. The Catalyst Optimizer selects the query path that results in the lowest time and memory consumption. Because queries can use multiple paths, these calculations can become quite complex when large datasets are part of the calculation. Consider the analogy of a car and your travels. A car owner can optimize the vehicle's performance with the right oil, tires, fuel, and so on. These actions are similar to rule-based optimization. When it's time to plan a travel route that can save both time and wear and tear on your car, those actions are a form of cost-based optimization. In the background, the Catalyst Optimizer uses a tree data structure and provides the data tree rule sets. To optimize a query, Catalyst performs the following 4 high-level tasks or phases: analysis, logical optimization, physical planning, and code generation. Let's review the 4 Catalyst phases. In the analysis phase, Catalyst analyzes the query, the data frame, the unresolved logical plan, and the catalog to create a logical plan. During the logical optimization phase, the logical plan evolves into an optimized logical plan. This is the rule-based optimization step of Spark SQL, and rules such as folding, pushdown, and pruning are applied here. During the physical planning phase, Catalyst generates multiple physical plans on the logical plan. A physical plan describes computation on datasets with specific definitions on how to conduct the computation. A cost model then chooses the physical plan with the least cost. This is the cost-based optimization step. The final phase is code generation. Catalyst applies the selected physical plan and generates Java bytecode to run on each node. Let's now examine how Tungsten provides cost-based optimization in Spark. Tungsten optimizes the performance of underlying hardware, focusing on CPU performance instead of I/O. Java was initially designed for transactional applications. Tungsten aims to improve CPU and memory performance by using a method more suited to data processing for the JVM to process data. To achieve optimal CPU performance, Tungsten applies the following capabilities. Tungsten manages memory explicitly and does not rely on the JVM object model or garbage collection. Tungsten creates cache-friendly data structures that are arranged easily and more securely using stride-based memory access instead of random memory access. Tungsten supports JVM bytecode on demand. Tungsten does not enable virtual function dispatches, reducing multiple CPU calls. Tungsten places intermediate data in CPU registers and enables loop unrolling. In this video, you learned that Catalyst is the Spark SQL built-in rule-based query optimizer. Catalyst performs analysis, logical optimization, physical planning, and code generation. Tungsten is the Spark built-in cost-based optimizer for CPU and memory usage that enables cache-friendly computation of algorithms and data structures. Welcome to Using Data Frames with Real-World Data. After watching this video, you'll be able to identify the basic data frame operational steps, apply basic data frame operations on real-world data, apply Spark data frames to real-world data. Let's begin with basic data frame operations: reading, analysis, transformation, loading, and writing. First, Spark reads in the data and loads the data into a data frame. Next, you can analyze the data set starting with simple tasks such as examining the columns, data types, number of rows, and optionally working with aggregated stats, trend analysis, and other operations. If needed, you can transform the data by filtering the data to locate specific values, sorting the data set based on specific criteria, or by joining this data set with another data set. Then you can load your transformed data set back to a database or a file system and write the data back to disk. This process is commonly also referred to as ETL, Extract, Transform, Load. ETL is an essential process in any data processing pipeline, as the first step makes data accessible to data warehouses for machine learning models, downstream applications, or other services. Let's talk about another standard process, ELT. Extract, load, and transform. This process emerged as a result of big data processing. With ELT, all of the data resides in a data lake. A data lake is a vast pool of raw data for which the purpose of the data is not predefined. When a data lake exists, each project forms individual transformation tasks as required, in contrast to anticipating all necessary transformation requirements usage scenarios as done with ETL and a data warehouse. Organizations often use a mixture between ETL and ELT. Let's take a closer look at each basic data frame operation. When reading the data, you can directly load data into data frames or create a new Spark data frame from an existing data frame. The displayed code sample shows how to load a dataset into a Pandas data frame in Python and then load the same dataset into a Spark data frame object. Let's continue the example that uses the dataset about car models and performance. This dataset contains columns for parameters such as miles per gallon, number of cylinders, horsepower, and other auto-related parameters. Here you can view the first few rows of the dataset. Next is analyzing the data. First, examine the data frame column data types or the schema using the print schema method. Take note of each column's data types. For example, the miles per gallon is a double type, while the first column indicates the car model name is a string. You can also examine a specified number of data frames using the show function. You can apply the select function to examine data from a specific column in detail. This example applies the select function to view the first 5 rows of the MPG column. After analyzing the dataset, your next step is to plan for any needed dataset transformations. The goal of a transformation is to retain only relevant data. Transformation techniques can include filtering the data, joining with other data sources, or performing columnar operations. Columnar operations are actions such as multiplying each column by a specific number, converting data from one unit to another, such as converting miles per gallon to kilometers per liter. Another common transformation technique is to group or aggregate data. Sometimes a downstream application may require aggregated data, such as a quarterly sales report that does not need to display every transaction, but needs to show the aggregated total quarterly sales and revenue numbers. Many transformations are domain-specific data augmentation processes. The effort needed can vary depending on the domain and the data. For example, scientific data sets involving multiple, differing measurements may require more columnar operations and unit conversions, while financial data can require more aggregation and averaging tasks. Here are some simple examples of transformations on the MT-CARS dataset. The filter function helps locate specific criteria within the dataset. In this case, the task is to filter the dataset for cars that have a mileage or MPG of less than 18 miles per gallon. Here is an example of aggregating data. In this example, the transformation aggregates all the records with the same number of cylinders, as seen in the CYL column, counts the number of vehicles with the specified number of cylinders, and sorts the data to list the number of units for each cylinder category in ascending order. We can see that 14 cars have an 8-cylinder engine and 11 cars have a 4-cylinder engine. The ETL pipeline's last step is to export the data to disk or load it into another database. Like reading the dataset and extracting the data, you can write the data to the disk as a JSON file or save the data into another database, such as a Postgres database. You can also use an API to export the data to another database, such as a Postgres database. In this video, you learned that basic data frame operations are reading, analysis, transformation, loading, and writing. You can use a pandas data frame in Python to load a dataset. You can apply the print schema, select function, or show function for data analysis. For transform tasks, keep only relevant data and apply functions such as filters, joins, column operations, grouping and aggregations, and other functions. Welcome to Apache Spark architecture. After watching this video, you'll be able to describe the architecture of Apache Spark, identify processes in a Spark application, explain how Spark jobs and tasks are related, define stages and describe when a data shuffle occurs. Describe the cluster deploy modes the driver program can be run in. A Spark application has two main processes. The driver program runs as one process per application. The driver process can be run on a cluster node or another machine as a client to the cluster. The driver runs the application's user code, creates work, and sends it to the cluster. An executor is a process running multiple threads to perform work concurrently for the cluster. Executors work independently. There can be many throughout a cluster and one or more per node, depending on configuration. The Spark context starts when the application launches and must be created in the driver before data frames or RDDs. Any data frames or RDDs created under the context are tied to it, and the context must remain active for the life of them. The driver program creates work from the user code called jobs, or computations that can be performed in parallel. The Spark context in the driver divides the jobs into tasks to be executed on the cluster. Tasks from a given job operate on different data subsets called partitions. This means tasks can run in parallel in the executors. A Spark worker is a cluster node that performs work. A Spark executor utilizes a set portion of local resources as memory and compute cores, running one task per available core. Each executor manages its data caching as dictated by the driver. In general, increasing executors and available cores increases the cluster's parallelism. Tasks run in separate threads until all cores are used. When a task finishes, the executor puts the results in a new RDD partition or transfers them back to the driver. Ideally, limit utilized cores to total cores available per node. For instance, an 8-core node could have one executor process using 8 cores. A stage in a Spark job represents a set of tasks an executor can complete on the current data partition. When a task requires other data partitions, Spark must perform a shuffle. A shuffle marks the boundary between stages. Subsequent tasks in later stages must wait for that stage to be completed before beginning execution, creating a dependency from one stage to the next. Shuffles are costly as they require data serialization, disk, and network I/O. This is because they enable tasks to pass over other dataset partitions outside the current partition. An example would be a group by, with a given key that requires scanning each partition to find matching records. When Spark performs a shuffle, it redistributes the dataset across the cluster. This example shows two stages separated by a shuffle. In stage 1, a transformation, such as a map, is applied on dataset A, which has two partitions, 1A and 2B. This creates dataset B. The next operation requires a shuffle, such as a group by. Key values could exist in any other partition, so to group keys of equal value together, tasks must scan each partition to pick out the matching records. Transformation results are placed in stage 2. Here, results have the same number of partitions, but this depends on the operation. Final results are sent to the driver program as an action, such as collect. Note, it is not advised to perform a collection to the driver on a large dataset, as it could easily use up the driver process memory. If the dataset is large, apply a reduction before collection. Let's recap what we've learned about Spark architecture. It consists of the driver and the executor processes. The cluster comprises the cluster manager and worker nodes. The Spark context schedules tasks to the cluster, and the cluster manager manages the cluster's resources. The driver program can be run in either client or cluster mode. In client mode, the application submitter, such as a user machine terminal, launches the driver outside the cluster. In cluster mode, the driver program is sent to and run on an available worker node inside the cluster. The driver must be able to communicate with the cluster while it is running, whether it is in client or cluster mode. In this video, you learned that Spark architecture has driver and executor processes coordinated by the Spark context in the driver. The driver creates jobs and splits them into tasks which can be run in parallel in the executors. Stages are a set of tasks that are separated by a data shuffle. Shuffles are costly as they require data serialization, disk, and network I/O. The driver can be run in either client or cluster mode. The client mode connects the driver outside the cluster, while the cluster mode runs the driver in the cluster. Welcome to Overview of Apache Spark Cluster Modes. After watching this video, you'll be able to identify different modes of running Apache Spark on a cluster, describe the components and benefits of each cluster mode, describe how to run Spark to connect with each cluster mode, describe how and when to set up a local Spark instance. The Spark Cluster Manager communicates with the cluster to acquire resources for an application to run. It runs as a service outside the application and abstracts the cluster type. While an application is running, the Spark context creates tasks and communicates to the cluster manager what resources are needed. Then the cluster manager reserves executor cores and memory resources. Once the resources are reserved, tasks can be transferred to the executor processes to run. Spark has built-in support for several cluster managers. A standalone cluster manager is included with the Spark installation. It's best for setting up a simple cluster. Apache Hadoop Yarn, or yet another resource negotiator, is a cluster manager from the Hadoop project. Apache Mesos is a general-purpose cluster manager that Spark can run with additional benefits. Finally, Kubernetes is an open-source system for running containerized applications. Spark Standalone comes packaged with the Spark installation, so there are no additional dependencies required to configure and deploy. Spark Standalone is specifically designed to run Spark and is often the fastest way to get a cluster up and running applications. A Spark standalone cluster has two main components, workers and the master. The workers run on cluster nodes. They start an executor process with one or more reserved cores. There must be one master available which can run on any cluster node. It connects workers to the cluster and keeps track of them with heartbeat polling. However, if the master is together with a worker, do not reserve all the node's cores and memory for the worker. To manually set up a Spark standalone cluster, start the master. The master is assigned a URL with a host name and port number. After the master is up, you can use the master URL to start workers on any node using bidirectional communication with the master. Once the master and the workers are running, you can launch a Spark application on the cluster by specifying the master URL as an argument to connect them. To see additional configuration options, refer to the Apache Spark documentation on the spark.apache.org website. Apache Hadoop Yarn is a general-purpose cluster manager. It's popular in the big data ecosystem and supports many other frameworks besides Spark. Yarn clusters have their own dependencies, setup, and configuration requirements, so deploying them is more complex than Spark standalone. To run Spark on an existing Yarn cluster, use the -- master option with the keyword Yarn. When Spark sees that the cluster manager type is Yarn, it will look for the standard Hadoop configuration files to decide how to connect with the Yarn cluster. No other configuration from Spark is needed. Apache Mesos is another general-purpose cluster manager supported by Spark. Using Mesos has some advantages. It can provide dynamic partitioning between Spark and other big data frameworks and scalable partitioning between multiple Spark instances. However, running Spark on Apache Mesos might require some additional setup depending on your configuration requirements. More details are provided on the spark.apache.org website at the link shown here. A Kubernetes cluster runs containerized applications. This makes Spark applications more portable and helps automate deployment, simplify dependency management, and scale the cluster as needed. Spark uses a built-in native Kubernetes scheduler. To run Spark on Kubernetes, use the example call shown. Local mode runs a Spark application as a single process locally on the machine. Executors are run as separate threads in the main process that calls spark-submit. Local mode does not connect to any cluster or require configuration outside a basic Spark installation. Local mode can be run on a laptop. That's useful for testing or debugging a Spark application. For example, testing a small data subset to verify correctness before running the application on a cluster. However, being constrained by a single process means local mode is not designed for optimal performance. To run in local mode, use the -- master option with the keyword local, followed by a number to indicate how many cores the Spark application can use for the executor. To use all available cores, replace the number with an asterisk wildcard. Keep in mind, not all configuration for a cluster will be valid in local mode. In this video, you learned that cluster managers acquire resources and run as an abstracted service outside the application. Spark can run on Spark Standalone, Apache Hadoop Yarn, Apache Mesos, or Kubernetes cluster managers with specific setup requirements. Choosing a cluster manager depends on your data ecosystem and factors such as ease of configuration, portability, deployment, or data partitioning needs. Spark can run in local mode, useful for testing or debugging an application. Welcome to How to Run an Apache Spark Application. After watching this video, you'll be able to describe how to submit an Apache Spark application. Explain the characteristics of Spark's unified interface, Spark-submit. Describe and apply the options you can use to submit applications. Describe ways of managing external application dependencies. Describe the benefits of using Spark Shell to run applications. Spark comes with a unified interface for submitting applications. It's the spark-submit script found in the bin directory. Spark-submit can be used for all supported cluster types and accepts many configuration options for the application or cluster. Unified interface means you can switch from running Spark in local mode to cluster by changing a single argument. Spark-submit works the same way, no matter the application language. For example, a cluster can run Python and Java applications simultaneously by passing in the required files. The Spark-submit script first parses any command line arguments or options. Then it reads any additional configuration specified in the Spark-defaults folder. Next, the -- master argument tells the application how to connect to the cluster or run locally. Any application files, including jars or Python files, must be specified so they can start the driver program and distribute files to run in the cluster. Some Spark-submit options are mandatory, such as specifying the master option to tell Spark which cluster manager to connect to. If the application is written in Java or Scala and packaged in a jar, you must specify the full class name of the program entry point. Other options include driver deploy mode, run as a client or in the cluster, and executor resource settings, such as reserving memory or cores. Driver deploy mode defaults to client mode. Some options relate to specific cluster managers. Additional Spark configuration can be specified on the command line using the --conf argument, followed by key equals value. For Java or Scala and Python, final arguments will be the path to the application jar or Python script. Next are optional application-specific arguments. These will automatically be passed in. You can add Python files with .py, .egg, or .zip using the --py-files argument. These files will be distributed to the cluster and available in the Python environment. Let's look at two Spark-submit examples. The first launches SparkPy, written in Scala and packaged in a jar. Yarn is the master. The application uses an additional argument, how many samples to take in the cluster to compute pi. The second example launches a SparkPy Python version. The master is a Spark standalone cluster, and we simply pass the path to the Python script. To manage Spark dependencies, the application project or library must be accessible for the driver and cluster executor processes. For a Java or Scala-based application, it's best to create an Uber jar. This is a single jar file with all dependencies, including transitive ones, so the application is portable throughout the cluster. For Python applications, ensure that 1. The cluster nodes access required dependencies with the same version, and 2. The same Python version is used. Solutions for Python dependencies may involve creating virtual environments so that applications can run in separate, isolated environments. Python dependencies can be included in the Spark-submit script using the --py-files argument. This will accept .py, .zip, or .egg files. Spark Shell is available for Scala and Python, giving you access to Spark APIs for working with data as Spark jobs. Spark Shell can be used in local or cluster mode, with all options available. When Spark Shell starts, the environment automatically initializes the Spark context and Spark session variables. This means you can start working with data immediately. Expressions are entered in the shell and evaluated in the driver. Entering an action on a shell data frame generates Spark jobs that are sent to the cluster to be scheduled as tasks. This example shows the Spark Scala shell starting up in local mode. The printout includes Spark's load log in the log4j-defaults.properties file, Spark's web UI address displaying running jobs in the shell, variable names for the initialized Spark context and Spark session, and version information for important libraries like JDK and Scala. This example shows running code in the Scala shell. In the first line, a data frame is created as a distributed range of integers from 0 to 9. The second line transforms the data frame, adding a column calculating the modulo of 2. Next is an action that prints out the first 4 records of the resulting data frame. In this video, you learned that Spark-Submit is a unified interface to submit the Spark application, no matter the cluster manager or application language. Mandatory options include telling Spark which cluster manager to connect to. Other options set driver deploy mode or executor resourcing. To manage dependencies, application projects or libraries must be accessible for driver and executor processes, for example, by creating a Java or Scala uberjar. Spark Shell simplifies working with data by automatically initializing the Spark context and Spark session variables and providing Spark API access. Welcome to the Apache Spark user interface. After watching this video, you'll be able to explain how to connect to the Apache Spark user interface web server, navigate basic elements of the Spark user interface. When a Spark application is being run, as the driver program creates a Spark context, Spark starts a web server that serves as the application user interface. You can connect to the UI web server by entering the host name of the driver, followed by port 4040 in a browser once the application is running. The web server runs for the duration of the Spark application, so once the Spark context stops, the server shuts down and the application UI is no longer accessible. The Spark user interface provides valuable insights organized on multiple tabs about the running application. The Jobs tab displays the application's jobs, including job status. The Stages tab reports the state of tasks within a stage. The Storage tab shows the size of any RDDs or data frames that persisted to memory or disk. The Environment tab information includes any environment variables and system properties for Spark or the JVM. The Executor tab displays a summary that shows memory and disk usage for any executors in use for the application. Additional tabs display based on the type of application in use. For example, if the application performs SQL queries, the SQL tab displays and shows metrics for each query. Let's take a closer look at the Jobs tab. The top of the window displays the event timeline and shows when the driver and executor processes start and when the jobs are created. In this example, the application has completed 2 jobs. These 2 jobs appear in the list at the bottom, which also has additional job-related information such as duration, number of stages, and number of total tasks for all stages. The job list also displays description hyperlinks to view the job details. Now let's view job details for information about the different stages of a specific job. The timeline displays each stage, where you can quickly see the job's timing and duration. Below the timeline display, you'll see completed stages. In the parentheses beside the heading, you'll see a quick view that displays the number of completed stages. Then, view the list of stages within the job and job metrics, including when the job was submitted, input-output sizes, the number of attempted tasks, the number of succeeded tasks, and how much data was read or written because of a shuffle. This example shows 2 stages separated by a shuffle. So, Stage 1 wrote shuffle data, and Stage 2 read that data. To view more details about a specific stage within a job, click the Stage ID description hyperlinks. The Stages tab shows a list of all stages in the application, grouped by the current state of either completed, active, or pending. This example displays 3 completed stages. Click the Stage ID description hyperlinks to view task details for that stage. The Storage tab displays details about RDDs that have been cached or persisted to memory and/or written to disk. This example image shows 1 RDD that's been cached to memory only. The Environment tab has several lists to describe the environment of the running application. These lists include the Spark configuration properties and resource profiles, as well as properties for Hadoop and the current system properties. The Executors tab displays a summary table at the top that shows metrics on all active or dead executors, along with a full range of metrics on the task numbers, data I/O, disk, and memory usage. At the bottom is a list of all executors, including the driver, that have been in use during the application, again with a full range of metrics. This list also provides links to the std_out and std_error log messages of the executor process. If the application runs SQL queries, the UI displays and populates the SQL tab. Click the SQL Description hyperlink to display the query's details. You can view the SQL query plan when you click the Details expander arrow. You can also view the query's DAG, including the logical physical plans as determined by the optimizer. In this video, you learned that the Jobs tab displays the application's jobs, including job status, and the Stages tab reports the state of tasks within a stage. The Storage tab shows the size of RDDs or data frames that persisted to memory or disk. The Environment tab information includes any environment variables and system properties for Spark or the JVM. The Executors tab displays a summary that shows memory and disk usage for any executors in use. If the application runs SQL queries, select the SQL tab and the Description hyperlink to display the query's details. Welcome to Monitoring Application Progress. After watching this video, you'll be able to define parts of the application workflow, utilize the UI web server to monitor application progress, describe a sample workflow from the UI. Running a Spark application can sometimes take a long time and have many possible points of failure. When an issue arises, say a faulty worker node is causing the occasional task to fail, it is essential to find and address the problem quickly so that cluster resources do not stay idle. The Spark application UI is a great way to monitor a running application. The application UI centralizes critical information, including status information, and organizes information logically, resulting in convenient and fast access. You can quickly identify failures, then drill down to the lowest levels of the application to find out the root causes of failures. Besides failures, the UI can also help you quickly locate and analyze application processing bottlenecks. A Spark application can consist of many parallel and often related jobs, including multiple jobs resulting from multiple data sources, multiple data frames, and the actions applied to the data frames. Workflows can include jobs created by the Spark context in the driver program, jobs in progress running as tasks in the executors, and completed jobs transferring results back to the driver or writing to disk. First, Spark jobs divide into stages, which connect as a directed acyclic graph, or DAG. Tasks for the current stage are scheduled on the cluster. When the stage completes all of its tasks, the next dependent stage in the DAG begins. The job progresses through the DAG. All stages are completed. If any of the tasks within a stage fail, after several attempts, Spark marks the task, stage, and job as failed and stops the application. Let's look at an example. The application first creates a job. Next, Spark divides the job into one or more stages. The first stage, stage 0, has no dependencies, so Spark sends its tasks to the executors. Stage 0 now has 2 tasks started. The width of the task indicates the elapsed runtime. 2 more tasks that are dependent on 0 and 1 run, but do not require a shuffle, such as map operations, for example, so they remain part of stage 0 and run independently. The end of stage 0 now marks the beginning of the next stage, 1. This boundary exists because a shuffle was required, which means that all tasks for stage 1 must wait for all tasks in stage 0 to finish before starting. Here you can see that tasks 4 and 5 have different runtimes. Their runtimes differ because each task is running independently and on different data partitions. However, the stage is not complete until all tasks have finished. With this job completed, Spark can begin a new job. In this example, job 1 depends on the data from job 0. The next job consists of one stage and starts tasks 6 and 7. Since tasks within a stage can run independently, when task 7 completes, the executor running task 7 can immediately start task 8 while task 6 continues to run. When the application completes tasks 8 and 9, the stage and job are complete, marking the end of this application workflow. Next, view this example application to see how the code translates to a workflow you can monitor using the UI. This application's single data source is a Parquet file loaded from disk to produce a data frame. Using that same data frame, 2 columns are selected. The caching action is specific to this example. The application groups the data by the country column and then aggregates the data by calculating the mean of the salary column. Next, the collect action runs. This action triggers the job creation and schedules the tasks, as the previous operations are all lazily computed. After you submit the application, start the Spark application UI and view the Jobs tab, which displays 2 jobs. One job reads the Parquet file from disk. The second job is the result of the action to collect the grouped aggregate computations to send to the driver. On the Jobs tab, click a specific job to display its Job Details page. Here you can see the number of stages and the DAG that links the stages. This example has 2 stages connected by a shuffle exchange, which is due to grouping the data by country in the application. Select a stage to view the tasks. The Stage Details timeline indicates each task's state using color coding. View the timeline to see when each task was started and the task's duration. Use this information to quickly locate failed tasks, see which tasks are taking a long time to run, and determine how well your application is parallelized. The task list provides even more metrics, including status, duration, and amount of data transferred as part of a shuffle. Here you see 2 tasks that read 1 and 2 records as part of a shuffle. You see these 2 tasks because, by default for a shuffle, Spark repartitions the data into a larger number of partitions. You can also access a task's executor logs. The data used in this example is small. Therefore, many tasks only have a small number of records to process. When all application jobs are complete and the results are sent to the driver or written to disk, the Spark context can be stopped either manually or automatically when the application exits. When the application UI server shuts down, the UI is no longer available. To view the application UI after the application stops, event logging must be enabled. This means that all events in the application workflow are logged to a file, and the UI can be viewed with the Spark History Server. To view the application UI with the History Server, first verify that event logging is enabled. Enter the event log path as seen using the properties displayed on screen before submitting the application. When the application completes, the application UI populates the log files in the event log directory. To start the History Server, apply the command shown on screen. Once the History Server is started, connect to the History Server by typing the History Server host URL, followed by the default port number 18080. You can see a list of completed applications and select one to view its application UI. In this video, you learned that the Spark application workflow includes jobs created by the Spark context in the driver program, jobs in progress running as tasks in the executors, and completed jobs transferring results back to the driver or writing to disk. The Spark application UI centralizes critical information, including status information. You can quickly identify failures, then drill down to the lowest levels of the application to discover their root causes. Welcome to Debugging Apache Spark Application Issues. After watching this video, you'll be able to identify common Apache Spark application issues, debug issues through the application UI, describe application log file locations and content, Running a Spark application on a cluster is a complex process with many working parts and many ways in which an application can fail. Common reasons for application failure on a cluster include user code, system and application configurations, application dependencies that are missing or an incorrect version, improper resource allocation, and network communication among cluster nodes. What is user code? User code is made up of the driver program, which runs in the driver process, and the functions and variables serialized that the executor runs in parallel. Both the driver and executor processes run the application user code of an application passed to the Spark submit script. The user code in the driver creates the Spark context and creates jobs based on operations to the data frames. These data frame operations become serialized closures sent throughout the cluster and run on executor processes as tasks. The serialized closures contain the necessary functions, classes, and variables needed to run each task. Spark usually immediately terminates when syntax, serialization, data validation, and other use errors occur. Spark reports task errors to the driver and immediately cancels the related executor tasks, terminating the application. For example, closures are cleaned before being serialized, flushing out most issues right away, and ensuring the closures can be serialized and executed remotely. User code serialized as a closure might not error until after the user code runs on another executor process. These errors could be due to runtime calculations, network communication issues, or unexpected data issues. If a task fails due to an error, Spark can attempt to rerun the task for a set number of retries. If all attempts to run the task fail, Spark reports an error to the driver and the application is terminated. The cause of an application failure can usually be found in the driver event log. A Spark application can have many dependencies, including application files such as Python script files, Java jar files, and even required data files. Applications also depends on the libraries used and their dependencies. Dependencies must be made available on all nodes of the cluster, either by pre-installation or by including the dependencies in the Spark submit script bundled with the application or as additional arguments. For example, a task will error if a Python library is not installed in the Python environment of the executor process. An even more subtle error can occur if a library is installed with different versions on executors that might have different APIs or produce unexpected results. The best way to identify this type of issue is by examining the event log for stack trace errors that identify which libraries the application loaded. Application resources such as CPU cores and memory can become an issue if a task is in the scheduling queue and the available workers do not have enough available resources to run the tasks. As a worker finishes a task, the CPU and memory in use are freed, allowing the scheduling of another task. However, if the application asks for more resources that can never become available, the tasks might never be run and eventually time out. Similarly, suppose that the executors are running long tasks that never finish. In that case, their resources never become available, which also causes future tasks never to run, resulting in a timeout error. You can readily access these errors when you view the UI or event logs. While the application UI provides a great deal of information, viewing the log files provides details that give more insights into possible application failure causes. You'll find the application log files in the Spark installation directory under work/application-id, where you will find one log file for stdout and one log file for stderr output. The application ID is a unique ID that Spark assigns to each application. These log files appear for each executor and driver process that the application runs. Additionally, if you're running a Spark standalone cluster, the master and workers both output log files to the log/directory under the Spark installation directory from where they run. In this video, you learned that common reasons for application failure on a cluster include user code, system and application configurations, missing dependencies, improper resource allocation, and network communications. Application log files will often show the complete details of a failure, which are located in the Spark installation directory. Welcome to Understanding Memory Resources for Apache Spark. After watching this video, you'll be able to describe memory parameters, describe Spark memory management, describe Spark data persistence, explain how to set executor memory on submit, explain how to set memory for Spark standalone memory and cores. When running a Spark application, the driver and executor processes launch with an upper memory limit. The upper memory limit enables a Spark application to run without using all the available cluster memory, but this limit also requires that the memory limits are set high enough to perform necessary tasks. An application runs best when processes complete within the requested memory. If the driver and executor processes exceed the memory requirements, this situation can result in poor performance with data spilling to disk or even out-of-memory errors. Let's examine some memory setting considerations for both executors and drivers. Executors use memory for processing and additional memory if caching is enabled. However, excessive caching can lead to out-of-memory errors. Collecting data as a result of operations will be done in the driver. Driver memory loads the data, broadcasts variables, and handles results, such as collections. Because large data sets can easily exceed the driver's memory capacity, if collecting to the driver, filter the data and use a subset of the data. In Spark, executor memory and storage memory share a unified region shown in this Java heap space in the space labeled M. When no executor memory is used, storage can acquire all the available memory and vice versa. Executor memory can evict storage memory if necessary, but only until storage memory usage falls under a certain threshold. In other words, R describes a subregion within M where cached blocks are never evicted. Storage is not allowed to evict executor memory due to complexities in implementation. This design ensures several preferable properties. First, applications that do not use caching can use the entire space for executor memory, obviating unnecessary disk spills. Second, applications that do use caching can reserve a minimum storage space, the area labeled R, where their data blocks are immune to being evicted. Lastly, this approach provides reasonable out-of-the-box performance for a variety of workloads without requiring user expertise of how memory is divided internally. Next, let's explore data persistence in Spark. Data persistence, or caching data in Spark, means being able to store intermediate calculations for reuse. By setting persistence in either or both memory and disk after the intermediate data is calculated to produce a new data frame, and if memory is cached, then any other operations on that data frame can reuse the same data, rather than reloading data from the source and recalculating all prior operations. This capability is essential to speed machine learning workloads that often require many iterations over the same data set when training a model. This sample PySpark code creates a data frame with column features consisting of random values. After creating the data frame, the cache method is called to mark the random values to cache in memory. Caching the data frame here means that the application only needs to generate random features once. At this point, the random values are not yet generated. Caching is done lazily after computing the values. In this example, the count action is invoked on the data frame, which generates the values that are then stored in memory. Subsequent data frame calls can use the cached values, which can save a great deal of computational time if the cost to recreate a data frame is high. If this data frame is not cached, then different random features would be generated with each action on the data frame because the function rand is called each time. There are several ways to set the memory for executors in a cluster, such as setting a value in the properties file. However, the more common practice is to specify a memory configuration when submitting the application to the cluster. You can tailor memory so that each application has enough memory to run effectively, but does not use all available memory in the executor. This example configures the application to run on a Spark standalone cluster and reserves 10 gigabytes per executor when running tasks. If using the Spark standalone cluster to manage and start a worker manually, you can specify the total memory and CPU cores that the application can use. These specifications determine the resources available when workers start the executors. Avoid assigning more resources than are available on the physical machine. For instance, if the machine has a CPU with 8 cores and the worker starts with 16 cores, too many threads might run simultaneously and cause performance degradation. You can tailor memory so that each application has enough memory to run effectively, but does not use all available memory in the executor. The default configuration is to use all available memory minus 1 GB for all available cores. In this video, you learned that Spark has configurable memory for executor and driver processes. Executor memory and storage memory share a region that can be tuned as needed. Caching data can help improve application performance. Welcome to Understanding Processor Resources for Apache Spark. After watching this video, you'll be able to explain how Apache Spark uses processor cores. Describe how to use Spark to configure cores for an application. Just as with memory, CPU cores are a resource assigned to both the driver and executor processes. An executor can process tasks in parallel only up to the number of cores assigned to the application. Once the application tasks finish processing, the cores no longer in use return to the available pool. The workers in the cluster contain a limited number of cores. If no cores are available to an application, the application must wait for currently running tasks to finish. When Spark launches an application and creates tasks, Spark places those tasks in a scheduling queue. Spark assigns tasks to any available executor. The default behavior is for each task that is ready to be scheduled to an executor with available cores to maximize parallelism. Any remaining tasks will have to wait in the queue until more cores become available. If you provided specific settings for the number of cores, such as configuring how many cores the executor uses, the application overrides the default behavior. To configure executor cores on application submission, use the argument --executor-cores, followed by the specific number of cores required for the application tasks to run on an executor. As always, if the executor does not have the required number of cores available, tasks do not start until the specified number of cores are free or another executor becomes available. Alternatively, the argument --total-executor-cores, followed by a number, is the total amount of cores throughout the cluster to use for the application, not per executor process. Tasks will be scheduled to executors whenever they have a free core until the total number of cores reaches the specified value. When starting a worker manually in a Spark standalone cluster, you can specify the number of cores the application uses by using the argument --cores followed by the number of cores. Spark's default behavior is to use all available cores. A common practice is to start one worker per node, which under default behavior allows the worker to create one executor process with exactly the same number of threads as cores available to run tasks. If another process is running on the same machine as the worker, such as the master, then a good practice is to apply these settings to reduce the number of cores available to the worker. Specifying the total number of CPU cores can reserve processing time available for the master process so essential operations are not blocked and timed out. Let's look at another example that uses a small standalone cluster with one worker node and 6 cores. This example uses 2 identical applications submitted to the same cluster in overlapping time, one right after the other. The first application is submitted to the cluster and requests 4 cores per executor. The executor is currently idle with 6 cores available. The first 4 tasks of the application are then scheduled to the executor and begin to run. 2 cores of the executor remain available. While the first application is running, the second application is submitted. The second application also requests 4 cores from the executor. Because tasks that belong to the first application are still running and are using 4 cores, only 2 cores are available. Therefore, the second application must wait until the executor has at least 4 cores available. As soon as any 2 tasks from the first application complete and 4 cores become available, the second application can begin. What if you start the second application and request only 2 cores to run 2 tasks? Using this scenario, you can submit a second application and 2 tasks immediately start. However, the second application might take longer to finish because of running only 2 tasks at a time. Maximizing Spark application performance can be a tricky balance between configuration of application workloads and cluster resources and requires careful tuning of both the application and the clusters. In this video, you learned that Spark assigns CPU cores to driver and executor processes during application processing. Executors process tasks in parallel according to the number of cores available or assigned by the application. If using the Spark Standalone Cluster Manager, you can specify the total memory and CPU cores workers can use.